The ground beneath you is red. Not the red of sunsets or autumn leaves, but a deep, mineral red, the color of iron baked for millions of years under a sky that has forgotten what clouds look like. You are standing somewhere in the middle of a continent so enormous it has no name yet, on a world that is slowly, quietly, tentatively beginning again. The air is warm. Not unpleasantly so, not the scorching furnace breath of the era just past, but a settled, dry warmth that sits against your skin like a memory of something hotter. There is no wind right now. The landscape around you is still in the way that only very old, very empty places can be still, a stillness so complete it has weight. In every direction as far as you can see, the land runs flat and rust-colored and empty. There are no mountains on this horizon, no forests crowding the skyline, no rivers catching the light. There is only the plain, stretching outward in every direction like something that has accepted its own enormity and stopped apologizing for it. The sky above is very large and very pale, the kind of pale that comes before a color has been decided. In the distance, a low range of hills, smoothed by time, sits against the horizon like a sleeping animal, patient and permanent. You breathe in. The air tastes of minerals and old heat and something faintly sweet that might be the distant suggestion of plant life beginning somewhere far away, somewhere nearer the coast where the rain still comes sometimes and the ground is willing to soften. Here, in the deep interior of the supercontinent, there is almost nothing. But almost nothing is not the same as nothing. And that is the entire point of the Triassic. Somewhere beneath your feet, pressed into the rock in layers you cannot see, is the record of everything that came before. The bones of animals so strange they barely seem possible. The shapes of forests that grew and fell and grew again over hundreds of millions of years. The chemical signatures of oceans that rose and retreated and changed their composition over timescales that make the word ancient feel inadequate. All of it is down there, recorded, preserved, waiting for someone to learn how to read it. Behind you, though you cannot see it from here, a world has just ended. Not in the dramatic way of asteroids and fire, though fire was certainly part of it. It ended slowly the way most things end, in accumulation. A little more heat each century. A little less oxygen in the water. A little more acid in the rain. Over 200,000 years, the Great Cascade consumed nearly everything that had learned to live on this planet, and what remains now is beginning to understand its inheritance. The sky shifts. A slow change in the quality of the light, the sun moving through its arc above the pale horizon. And then, across the flat red ground, you notice something that was not there before. Tracks. Three-toed impressions pressed into a patch of dried mud near a shallow depression that might, in wetter seasons, hold a pool of water. Something was here recently. Something walked across this empty plain and left its mark and moved on. You look out across the red plain and you see movement. Something small moving quickly low to the ground. It pauses at a rock, turns its head, and you catch the glint of a bright, watchful eye. It is nothing you would recognize. Nothing you have a name for. But it is alive, and it is curious, and somewhere inside the warm architecture of its small body, the future is being assembled one heartbeat at a time. Above the rock, above the red soil, above the stillness, life is beginning the slow and patient work of filling the world again. 252 million years of accumulated complexity has been stripped back nearly to nothing, and in the silence left behind, something extraordinary is about to happen. This is the Triassic, and it is only just beginning. Let yourself settle. Whatever the day held for you, whatever noise and motion and obligation filled those hours, let it soften now. You are about to travel somewhere very far away, not in distance but in time. 252 million years, give or take. Far enough that the continents you know do not exist. Far enough that the animals you know have not yet been imagined by evolution. Far enough that the very air you breathe would be subtly, strangely different from the air outside your window right now. If you enjoy listening to sleepy prehistoric dinosaur stories like this, subscribe. I post stories like this weekly, and there is always somewhere new to go, always another ancient world waiting in the dark. The story of the Triassic is not a simple one. It is not a story of triumph, though triumph is part of it. It is not a story of disaster, though disaster is certainly present. It is, more than anything, a story of persistence. Of life finding the thinnest possible threads of continuity through the most extreme conditions our planet has ever produced, and then, with extraordinary patience, weaving those threads into something new. Before the Triassic there was the Permian. The Permian was a world of established things. It had its rulers, its ecosystems, its deep grooves of survival worn smooth by millions of years of repetition. The oceans were full. The land was dominated by animals called synapsids, creatures that were not quite reptiles and not quite mammals but something ancient and successful in their own right. They had flourished. They had diversified. They had, in their way, achieved something close to permanence. And then the ground opened up. In what is now Siberia, the crust of the earth fractured along lines of weakness that had been building for longer than any living thing could comprehend. Magma rose. Not from cone-shaped mountains but from long, gaping rifts in the surface. Flood basalts pouring across the landscape in waves that continued for 2 million years. The gases that came with that lava, the carbon dioxide, the sulfur dioxide, the methane, rose into an atmosphere that had no way to neutralize them, and the world began to cook. By the time the eruptions slowed, roughly 96% of all marine species were gone. On land, perhaps 70% of vertebrate species had vanished. The forests were dead. The soils were toxic. The oceans in many regions had become low-oxygen dead zones where only the most primitive bacteria could survive. Geologists call this event the Permian-Triassic extinction. Paleontologists sometimes call it the Great Dying. Both names are accurate, but neither quite captures the scale of the silence that followed. What remained was almost nothing. And from almost nothing, the Triassic would build a world. Consider what that means for a moment. When you strip a planet nearly bare of its complexity, when you silence the forests and empty the oceans and leave only the most resilient and the most fortunate, you do not simply get a diminished version of what was there before. You get something new. The survivors of a catastrophe do not simply rebuild what was lost. They build what they are capable of building from what they have, in the conditions they find. And the Triassic conditions, extreme as they were, pointed evolution in directions it might never have explored otherwise. The early Triassic was a stark and difficult place, hot beyond almost anything that came before or after, its ecosystem simple and fragile, its survivors few and cautious. The Middle Triassic was a period of cautious diversification, life testing its footing on ground that had recently tried to kill everything. And the Late Triassic was something else entirely. Something strange and rich and full of experiments that would change the direction of life on Earth forever. The Triassic is the age when everything we think of as the Mesozoic began. The first dinosaurs. The first true mammals. The first flying vertebrates, the first crocodilians, the first turtles in recognizable form, the first complex marine reptile ecosystems. In 250 million years of complex animal life on Earth, very few periods can claim as many beginnings as the Triassic. And running through all of it, connecting the catastrophic beginning to the extraordinary end, is the thread of continuity. The fact that life did not stop. That in the lava-scorched, acid-drenched, oxygen-depleted world of the earliest Triassic, something was still moving. Something was still eating, still reproducing, still responding to the ancient chemical signals that say survive. That persistence, quiet and undramatic and absolutely fundamental, is what the Triassic is really about. The nights on the early Triassic plain were very long and very dark. The cloud cover from lingering volcanic activity dimmed the stars. The animals that were abroad in that darkness were small and cautious, moving close to the ground, alert for threats. They did not know they were the inheritors of a shattered world. They did not know that 50 million years later their distant descendants would include creatures that shook the earth with their footsteps. They only knew the warmth of the rock under their feet, the smell of the dry air, the particular quality of the darkness around them. This is their story. The story of the survivors and the inheritors, of the creatures that rebuilt a world from ash and silence and eventually filled it with a grandeur that would last for another 165 million years. Settle in. Close your eyes if you like. The red earth is beneath you, the warm air is all around, and somewhere out on that ancient plain, something small and fast is learning what it means to be alive in a world that is only just beginning to understand itself. You are standing at the edge of what was, very recently, a forest. You can tell because the ground is still shaped by it. Root channels have left their impressions in the hardened soil, long curving furrows that trace the memory of trees that no longer stand. There are no stumps. Whatever stood here did not fall, it simply ceased, its organic matter consumed by the chain of catastrophes that swept through this part of the supercontinent Pangaea in the centuries following the Great Volcanic Crisis. What remains is a kind of negative space, the shape of a forest without any of its substance. The sky above you is not blue. It is a pale, washed-out color, somewhere between gray and the faintest possible yellow, the residue of volcanic aerosols that have been drifting in the upper atmosphere for longer than most of the surviving animal lineages have been alive. The sun is present but softened, its light distributed evenly across the landscape without shadow. There is something unsettling about a shadowless world. Something that makes the spaces between objects feel indistinct, as if the ground and the air have not quite finished negotiating where one ends and the other begins. The temperature is high. Not lethally so, not in this particular moment, in this particular season, at this particular latitude, but high in the way that a room with no ventilation is high, a steady, unrelenting warmth that has nowhere to go. The Triassic world, particularly its early chapters, was warmer than anything in human experience. Global average temperatures in the early Triassic were perhaps 8 to 10 degrees Celsius above modern norms, and in the equatorial regions even higher. There were essentially no polar ice caps. The deep ocean was warmer than today's tropical seas. This warmth was not comfortable. It was the warmth of a world still processing the consequences of the volcanic catastrophe, still working through the excess carbon dioxide that had been pumped into the atmosphere over the previous 2 million years. The feedback loops that had amplified the original warming were still running, still adding degrees to a planet that had already exceeded any reasonable threshold. Life was not thriving in this warmth. It was enduring it. Walk forward across the red ground and feel the heat of it through the soles of your feet. The surface is not merely warm from the day's sun, it has been warm continuously for centuries, a geological warmth that goes deeper than a single season's heat. The rocks here have been baked to a reddish oxide by the long accumulation of oxidizing conditions in a world where the organic matter that used to consume atmospheric oxygen has been so drastically reduced that the oxygen itself now reacts with iron minerals in the rock, painting the landscape in the colors of rust and dried blood. The equatorial belt, that broad band around the planet's middle that in other eras was the cradle of biodiversity, was largely lifeless. Temperatures there regularly exceeded 50 degrees Celsius. Nothing could survive in the open. The rocks there were bare. The soil, where it existed at all, was baked to a hardness that made it nearly impermeable to water, which meant that on the rare occasions when rain did fall, it ran across the surface in sheets rather than soaking in, carrying whatever thin layer of mineral sediment existed down toward the lowlands and flash floods that left nothing behind. Life, in the early years of the Triassic, had retreated to the margins. The higher latitudes, where temperatures were merely hot rather than lethal. The coastal fringes, where ocean moisture moderated the worst extremes. The narrow corridors along river channels, where water made occasional existence possible. These were the refugia, the scattered islands of survivability in a largely hostile world, and in them the fragments of what had survived the extinction were slowly, haltingly, beginning to do what life always does. They were beginning to adapt. The survivors were a strange collection. Many of the dominant groups of the Permian were simply gone. Trilobites gone. The great synapsid dynasties, nearly gone, reduced to a handful of lineages clinging to existence in the higher latitudes. The complex reef ecosystems of the Permian oceans, gone. The diverse forests of seed ferns and primitive conifers, largely gone, replaced in many regions by a near monoculture of a single fern species, the Dichroidium, which had survived because of its particular combination of rapid reproduction and drought tolerance. What remained on land was dominated by a few groups of relatively simple animals. Small reptiles, mostly insect-eaters and small carnivores that could survive on the limited food resources available in the stripped-down ecosystems. Dicynodonts, barrel-shaped herbivores that had somehow survived the extinction against all odds, were among the most common large animals, grazing on the sparse vegetation with their turtle-like beaks. Archosaurs, the broad group that would eventually include dinosaurs, crocodilians, and pterosaurs, were present but not yet dominant, small and marginal and scattered across the landscape like the survivors they were. The recovery of the early Triassic was punctuated rather than smooth. There were periods when things seemed to be improving, when diversity was rising and ecosystems were knitting together into something approaching functional complexity, and then there were setbacks, smaller extinction events triggered by the continued instability of the climate system, each one resetting parts of the recovery that had been painstakingly achieved. This pattern of advance and retreat, of progress interrupted by setback, defined the ecological history of the early Triassic in a way that made the recovery far slower than the mere passage of millions of years might suggest. In the oceans, the situation was in some ways even more dire. The Permian Triassic extinction had hit marine life especially hard, eliminating perhaps 96% of marine species. The oceans of the early Triassic were in many regions hypoxic or even anoxic, their water columns depleted of oxygen by the combination of warming temperatures and the altered chemical cycling that the extinction had produced. Fish and other mobile marine animals could survive by staying in the oxygenated surface layers, but the bottom communities that had been so rich and diverse in the Permian had been largely eliminated. The smell of those early Triassic oceans would have been distinctive and unpleasant. The deep water, where anaerobic bacteria processed the enormous quantities of organic matter that the extinction had produced, was generating hydrogen sulfide in quantities that occasionally upwelled to the surface, giving the coastal waters a sulfurous edge. This same hydrogen sulfide, in high enough concentrations, is toxic to most aerobic life, and some researchers have suggested that it contributed to coastal and nearshore extinctions in the immediate aftermath of the Permian-Triassic event. The land was also chemically stressed. The acid rain that had been a feature of the extinction period continued at reduced intensity in the early Triassic, its sulfuric acid content having leached nutrients from soils and disrupted the chemistry of rivers and lakes. The soils themselves, deprived for centuries of the input of organic matter from living plants, had lost much of the biological activity that makes soil productive, the fungi and bacteria and invertebrates that break down organic matter and cycle nutrients back into forms plants can use. Without this biological infrastructure, even the plants that managed to establish themselves in the early Triassic were growing in conditions that limited their productivity. And yet life persisted. The persistence of life through the early Triassic is, in its quiet way, as extraordinary as any of the more dramatic evolutionary developments that came later. The organisms that survived did so not through any particular excellence, not through the development of impressive new structures or behaviors, but through the sheer stubborn continuity of biological process. The capacity of living systems to keep running even at severely reduced efficiency, to keep reproducing even when conditions make reproduction difficult, to keep evolving even when the selection pressure is primarily toward elimination. There was one group of organisms that actually thrived in the post-extinction conditions, that found in the ecological devastation a set of conditions that suited them perfectly. The microbial mats, communities of bacteria and cyanobacteria that form flat, layered structures in shallow water and on moist surfaces, expanded dramatically in the early Triassic. These organisms, which had been subdominant in the complex ecosystems of the Permian, found themselves in a world where their primary competitors, the animals and plants that normally graze on them and compete with them for resources, had been drastically reduced. The microbial mat communities that are recorded in early Triassic rock formations are a reminder that the history of life is not always a story of increasing complexity. Sometimes complexity retreats, and the simplest systems reassert themselves. The early Triassic lasted roughly 4 to 5 million years. This is a significant span of time by human reckoning, long enough for a great deal to happen, but by geological standards it was a relatively brief period of recovery and consolidation. During these years, the global temperature remained extremely elevated, and the periodic pulses of anoxia, regions of the ocean deprived of oxygen, continued to stress marine ecosystems in ways that prevented full recovery. There were multiple smaller extinction events within the early Triassic itself, aftershocks of the Great Dying that kept resetting the clock on recovery whenever a group of species began to establish itself. And yet, in the margins, in the refugia, in the narrow bands of survivable habitats scattered across the hot face of Pangaea and the equally hot surface of the Panthalassic Ocean that surrounded it, things were happening. Mutations were accumulating. Natural selection was working its patient arithmetic on the populations of survivors. Species were discovering new food sources, new habitats, new ways of processing the difficult world they inhabited. One of the most important developments of this early period was the proliferation of what paleontologists sometimes call disaster taxa, species that are particularly well suited to exploiting disturbed and simplified ecosystems. These are typically generalists, animals capable of eating a wide variety of foods, surviving in variable conditions, reproducing quickly. They tend to dominate after mass extinctions the way weeds dominate after a field is cleared, not because they are the most sophisticated or the most specialized, but because their very lack of specialization makes them resilient. Among the disaster taxa of the early Triassic, one group is particularly significant for our story. The archosaurs were not yet the imposing creatures they would become. Early Triassic archosaurs were mostly small, fast-moving, insectivorous or small carnivore animals with an upright or semi-upright posture that made them more energetically efficient than many of their competitors. They were not dominant. But they were adaptable, and in a world where adaptability was the primary currency of survival, this mattered enormously. Somewhere in the scattered populations of early archosaurs moving across the margins of the early Triassic world, the lineages that would eventually give rise to dinosaurs were already beginning to diverge from those that would give rise to crocodilians. The split was not dramatic. No observer at the time, had any been present, would have noticed a meaningful difference between the various small archosaurs scratching for insects in the red dust of post-extinction Pangaea. But the differences were there, small and accumulating, chromosomal instructions being revised by natural selection one generation at a time. The early Triassic world was a quiet world. Quiet in the biological sense, with fewer species producing fewer sounds, fewer interactions, fewer complex chains of dependency between organisms. The buzzing richness of a healthy ecosystem, the constant signaling and responding and competing and cooperating that fills every living landscape with noise, was largely absent. There were insects and they buzzed. There were frogs and early amphibians near the water and they called. There were the small reptiles moving through the sparse vegetation, rustling and scratching. But compared to what had come before or what would come after, the early Triassic soundscape was muted. This quietness was not peaceful exactly. It was the quietness of a room after something has happened in it, a quietness full of awareness and adjustment. The surviving creatures were not relaxed. They were vigilant, opportunistic, constantly testing the boundaries of what their particular versions of existence could support. The world was not resting. It was calculating. And then, slowly, almost imperceptibly at first, the temperature began to come down. The volcanic systems that had driven the crisis were finally exhausting themselves, their magma chambers emptying, their eruptions becoming less frequent. The atmosphere, which had been struggling to process the enormous carbon dioxide load it had been handed, was beginning, through the slow chemistry of rock weathering and ocean absorption, to pull some of that burden back down. The sky, perhaps, was very gradually becoming less yellow. The shadows were returning, faint at first but present. The Middle Triassic was not yet a world anyone would call lush. But it was a world where the ceiling had been raised slightly, where the edge of lethality had moved back a fraction, where a species with a reasonably flexible diet and a reasonably efficient body plan could, for the first time since the Great Dying, begin to do something other than simply survive. It could begin to expand, to diversify, to explore the emptied ecological landscape that the extinction had left behind and find, in all those empty niches, something like opportunity. The red ground beneath you is still red. The air is still warm. But somewhere in the distance, something is moving with more purpose than it had before. Something is learning the shape of a world that is very slowly, very quietly, becoming possible again. The silence is still here, but it has a different quality now. Not the silence of devastation, but the silence of potential, of held breath, of the moment before something begins. The relationship between the surviving plant communities and the animals that depended on them was strained in the early Triassic in ways that went beyond simple scarcity. The chemical composition of the vegetation that survived the extinction was different from what had preceded it. The Permian had supported complex forests with dozens of tree species, each producing leaves with different nutritional profiles, different defensive chemicals, different structural properties. The post-extinction vegetation was much simpler, dominated by a few fast-colonizing species whose leaves were often high in defensive compounds and low in easily digestible nutrients. Herbivores that had evolved to process the richer, more diverse Permian flora found themselves in a world where their food was simultaneously scarce and of poor quality. Water chemistry in early Triassic rivers and lakes was also unusual. The disruption of weathering cycles during the extinction had altered the balance of minerals being carried into freshwater systems, and some of the anoxic pulses that affected the oceans had freshwater equivalents in enclosed basins. Fish and amphibians living in these systems were subject to periodic die-offs when oxygen levels dropped, creating cycles of local extinction and recolonization that kept freshwater communities simple and unstable for millions of years. The persistent instability of freshwater habitats in the early Triassic was one of the factors that delayed the recovery of complex freshwater ecosystems until well into the Middle Triassic. The relationship between the early Triassic atmosphere and the biology of the surviving organisms was not merely a matter of temperature. The slightly elevated oxygen levels of the Permian had declined slightly by the early Triassic, though not dramatically, and the elevated CO2 was a genuine stress for some organisms. Modern experiments with elevated CO2 environments show that plants and animals respond in complex ways, some thriving and some struggling, and the early Triassic atmosphere was a filter that selected for the particular physiological tolerances of each group in ways that shaped the subsequent evolution of all lineages that survived it. The rock layers from the early Triassic record this extreme world with unusual clarity. The sediments are strikingly simple in their composition compared to the complex, bioturbated sediments of periods with healthy ecosystems. When organisms are abundant and diverse, they mix sediments as they burrow and feed and move, creating a blended, churned appearance in the geological record. Early Triassic sediments are often laminated, laying down in thin, undisturbed sheets, because there was almost nothing alive in them to disturb the deposition. The absence of bioturbation is itself a record of devastation, a silence written in stone. The chemistry of early Triassic ocean sediments preserves the record of the recovery in detail. Isotopic signatures of carbon and sulfur track the slow normalization of ocean chemistry as the volcanic inputs declined and the biological pump, the cycling of carbon through living organisms from surface water to deep sediment, gradually re-established itself. The time required for the ocean to return to something approaching its pre-extinction chemical state is estimated at 5 to 10 million years from the peak of the crisis, a measure of the depth of the disruption that the Great Dying had caused. The terrestrial survivors of the Great Dying faced the task of rebuilding soil communities that had been devastated by the extinction of so many plant and animal species. Soils are complex ecosystems in their own right, their structure and fertility dependent on the activities of earthworms, fungi, bacteria, and other organisms that process organic matter and cycle nutrients. When the organisms that build and maintain soil ecosystems go extinct, the soils themselves degrade, their structure collapsing, their fertility declining, their capacity to support plant growth diminishing. The rebuilding of functional soil communities was one of the most important and least visible aspects of the early Triassic recovery. If you are drifting now, let yourself go. There is more of this world waiting for you, and the next chapter will be here when you return. Consider subscribing so the next story is. Close your eyes for a moment and try to imagine the world without its oceans. Not empty, not dry, just simplified, reduced to its essential skeleton of rock and sediment. Now take all the land that exists and press it together, the way you might gather scattered pieces of a puzzle toward the center of a table, pushing continents that have been drifting apart for the last 200 million years back together into one enormous mass. This is Pangaea, and it is the stage upon which everything that happens in the Triassic is performed. Pangaea was extraordinary. Not merely large, though it was certainly that, a single landmass stretching from the North Pole to the South Pole, covering roughly a third of the Earth's surface. Its extraordinariness lay in what that size and configuration meant for the planet's climate, for its weather systems, for the distribution and character of its living things. There has never been, in the entire history of complex animal life on Earth, another landmass quite like it, and there will likely never be another. You are standing somewhere in the middle of it now. This is the interior, the vast heartland of Pangaea, and it is not a forgiving place. The nearest coast is perhaps 2,000 kilometers away in any direction. The ocean, that great moderator of temperature and provider of moisture, cannot reach you here. The air that arrives at this point has had all of its water wrung out of it over thousands of kilometers of travel across sun-baked rock and sand. It arrives dry and hot and it leaves the same way. The landscape around you is not featureless. There are gentle ridges of ancient rock, eroded down to smoothness over hundreds of millions of years, their surfaces stained in shades of ochre and burnt sienna by the iron oxides that accumulate when rock weathers slowly in dry air. There are shallow depressions that, during the wet season, hold water for a few weeks at a time before evaporating back to cracked mud. There are the sinuous traces of occasional watercourses, dry for most of the year, marked by slightly more vegetation along their banks, thin lines of green threading through the red and orange of the broader landscape. But mostly there is space. A tremendous, flat, reddish space that extends to the horizon in every direction, and beyond the horizon to more of the same. The sky above is vast in proportion, a dome of blue that in this latitude in this season contains no clouds at all. The sun tracks across it with the unhurried authority of a thing that knows nothing has the standing to question it. The shadows of the few low rocks in the vicinity are short and sharp and move almost imperceptibly as the morning progresses, marking time in the ancient way. The interior of Pangaea experienced one of the most extreme climates in Earth's history. The temperature swings between day and night were enormous because there was no moisture in the air to moderate them. During the day, the ground absorbed heat from the sun and the air temperature rose to levels that would kill most modern animals within hours if they could not find shade. At night, with no cloud cover and no humidity to trap the warmth, temperatures plummeted with startling speed, sometimes dropping 30 or 40 degrees Celsius within a few hours of sunset. This thermal cycling was not merely uncomfortable. It was architecturally significant. Rock that is heated and cooled through large temperature ranges expands and contracts, and over thousands of years this expansion and contraction fractures even the hardest stone, reducing it to progressively smaller fragments. The interior of Pangaea was slowly grinding itself to dust, producing vast quantities of fine sediment that the seasonal winds carried across enormous distances, building dune fields and loess deposits that in some regions reached hundreds of meters in depth. The wind itself was a defining feature of the Pangaean interior. Without the friction of forests or complex topography to slow it, Wind could build to extraordinary velocities across the flat interior plains. Dust storms of a scale that has no modern equivalent would have swept across the landscape for days at a time, filling the air with fine particles that turned the sky a uniform orange-brown and reduced visibility to nearly nothing. Animals caught in the open during such storms had few options. They pressed themselves against rocks or burrowed into whatever shelter the landscape offered and waited. There is a patience in this landscape that is different from the patience of a forest or a sea. The forest is patient in a living way, its patience the accumulated stillness of organisms that move slowly. The sea is patient in a moving way, its patience the continuity of motion through countless repetitions. But the interior of Pangaea is patient in a mineral way, a geological patience that has nothing to do with life at all, that predates life and will outlast it, the patience of rock and sand and time. Along the coasts of Pangaea the climate was different. Very different. The ocean provided moisture, and where moisture was available, life organized itself with a richness that stood in sharp contrast to the empty interior. The coastal fringes of Pangaea during the Triassic supported forests, though not forests that would be familiar to modern eyes. These were forests of early conifers and seed ferns, of cycads and tree ferns, their canopies not the interlocking green cathedral of a modern tropical forest but something sparser and stranger, shaped by the particular challenges of a Triassic growing season. The great monsoon systems of Pangaea were another defining feature of its climate. The enormous size of the landmass created temperature differentials between land and sea that drove atmospheric circulation on a continental scale. During summer in the northern hemisphere, the interior of Pangaea heated dramatically, creating a massive low-pressure system that drew moist air inland from the Tethys Sea, the great ocean arm that divided Pangaea roughly in half along its equatorial belt. This moist air dropped its water as it rose over coastal highlands, producing seasonal rains of tremendous intensity. The monsoons were not gentle things. They were months-long inundations that transformed dry river channels into raging torrents, that submerged coastal lowlands under meters of water, that stripped topsoil from hillsides and redeposited it as vast sediment fans in the flatlands below. Then, as winter arrived and the temperature differential reversed, the monsoons retreated, the rains stopped, and the long dry season began. Organisms living along the coasts of Pangaea had to be capable of surviving both extremes, the drowning excess of the wet season and the parched privation of the dry. These seasonal extremes created a particular evolutionary pressure that defined the character of Triassic life for millions of years. The most successful organisms were not those optimized for either the wet or the dry condition exclusively, but those capable of shifting strategies as conditions changed. Plants that could grow rapidly during the monsoon and then survive drought through stored water or deep root systems. Animals that could exploit the abundance of the wet season and endure the privation of the dry through behavioral or physiological flexibility. The harsh seasonality of the Pangaean coasts was, paradoxically, a powerful engine of evolutionary creativity. The Tethys Sea itself was a remarkable feature. This warm, shallow inland sea occupied the space between the northern half of Pangaea, sometimes called Laurasia, and the southern half, Gondwana. It was warm because of its latitude and because it was partially enclosed, its circulation limited in ways that trapped solar heat. Its warmth made it biologically productive, and as the Triassic progressed and marine life recovered from the Great Dying, the Tethys would become one of the most biodiverse marine environments on the planet. The shallow shelves along the Tethys margin were particularly important for the recovery of marine ecosystems. These were the zones where sunlight could penetrate to the seafloor, where nutrients washed from the land supported dense blooms of photosynthetic organisms, where the complexity of the substrate created shelter and feeding opportunities for a wide variety of animals. The earliest post-extinction reef-building organisms began their recovery in these shallow Tethys margins, slowly over millions of years, reconstructing something approximating the complex three-dimensional habitats that the Great Dying had destroyed. On the western side of Pangaea, facing the vast Panthalassic Ocean that covered nearly two-thirds of the planet's surface, the conditions were different again. The Panthalassic was simply enormous, a world ocean so large that its internal circulation operated on scales that had no modern analogy. Without continents to interrupt its gyres, currents could circle the globe unimpeded, and the interaction of these currents with the western margins of Pangaea produced its own distinctive coastal climate, different from the Tethys side, shaped by upwelling cold water from the deep ocean and the particular wind patterns generated by the massive temperature differential between ocean and land. The geography of Pangaea was, in short, a geography of extremes. The interior was among the most hostile places on the planet's surface. The coasts were productive but volatile. The shallow Tethys was a crucible of marine evolution. The vast Panthalassic was a planetary regulator whose behavior influenced weather patterns across every part of the landmass. Everything that lived in the Triassic lived inside this system of extremes, shaped by it, adapted to it, eventually transformed by it. As the Triassic progressed, Pangaea was already beginning to crack. The forces that had assembled it were being replaced by new forces that were pulling it apart. Deep in the mantle, convection currents were redirecting hot plumes of rock rising under sections of the continent's crust and heating it from below, causing it to swell and rift. These rifts were still small in the early and middle Triassic, shallow valleys rather than oceans, but they were the first signs of the continental breakup that would eventually produce the world we know today. The rifting would have its own effects on climate. As new ocean basins opened, even narrow ones, they created new corridors for water circulation, new sources of moisture, new moderating influences on the brutal continental climate of the interior. The world was not static. It was changing slowly but inexorably, and the life that inhabited it was changing with it. The rifts themselves were not merely geological features. They were habitats, the valleys they created collecting water from the elevated edges, producing river systems that ran through otherwise dry terrain. The earliest rifts of Pangaea, those shallow depressions that prefigure the eventual Atlantic Ocean, were lined with vegetation in ways that the broader interior was not, their lower elevation and higher moisture creating a biological richness that stood out against the surrounding desolation. There is something humbling about standing in the interior of Pangaea and trying to conceive of its extent. The distances involved are not merely large by the standards of human travel. They are large by the standards of animal migration, by the standards of the range of individual species, by the standards of anything that moves through the world on legs or wings. This is a continent that a fast-running animal could spend its entire life crossing without reaching the other side. A continent that contains within it every possible terrestrial habitat from polar tundra to equatorial desert. A continent that is, in a very real sense, an entire world unto itself. You stand on the red plain and you feel the warmth and the dryness and the immensity of the space around you. You are inside a continent that is in the process of becoming something else. The cracks that will eventually split it into pieces are already forming underfoot, invisible but real, the future pressing up through the ancient rock like the first green shoots after a long winter. Everything about this landscape seems permanent. Nothing about it is. The very ground you stand on is moving, slowly but without cessation, carried on a raft of rock that is drifting toward configurations that will not be complete for another 200 million years. And yet this impermanence does not diminish the reality of the moment. The heat is real. The silence is real. The distant sound of wind moving across rock, a sound so dry it barely registers as sound at all, is real. This landscape, alien as it is a real place, a real time, a real world that existed as completely and as fully as the world outside your window right now. Let that be something to hold on to as you breathe in this ancient air and feel the old ground beneath you and listen to the Triassic silence settling over everything like fine red dust. The geophysics of Pangaea created circulation patterns in the upper atmosphere as well as at the surface. The enormous temperature contrast between the heated continental interior and the cooler oceanic margins drove jet stream-like flows in the upper troposphere that had no modern equivalent, simply because no modern continent approaches the size and the thermal mass of Pangaea. These upper atmospheric flows influenced the distribution of clouds and precipitation in ways that reinforced the extreme continentality of the interior while concentrating moisture along the coasts. The Pangaean atmosphere was a system whose behavior emerged from the specific geometry of one enormous continent surrounded by one enormous ocean. The magnetic field of the Earth during the Triassic was similar in its broad outlines to the modern field, with a north and south magnetic pole roughly aligned with the rotational poles, but it differed in details that influenced the animal life of the time in ways we can only partially reconstruct. Migration in modern animals is partially guided by magnetic sense, and if Triassic animals had similar capabilities, the specific configuration of the Triassic magnetic field would have shaped their migratory routes and patterns. The Triassic fossil record includes some evidence of long-distance movement by certain species, and the magnetic field may have been one of the navigational tools available to animals making these journeys. The tidal patterns of the Triassic world were different from those of the modern ocean in ways that are rarely considered but were ecologically significant. Tidal ranges are determined by the geometry of ocean basins, the resonance between the gravitational forcing of the moon and sun and the natural oscillation periods of the water bodies in which tides propagate. The single enormous ocean of Pangaea, the Panthalassic, had resonance characteristics very different from those of the multiple separated ocean basins of the modern world, and the tidal patterns that resulted were unlike anything in the current configuration. Coastal organisms evolved around these Triassic tidal regimes, and the intertidal and subtidal communities of the Triassic were structured by the particular rhythms of water rise and fall that characterized the Panthalassic margins. The deep circulation of the Panthalassic Ocean was driven by the same basic thermohaline processes that drive modern ocean circulation, the sinking of cold, dense water in high latitudes and the compensating upwelling of deep water in other regions, but the specific patterns of this circulation were very different from the modern Atlantic and Pacific circulation systems. The absence of continental barriers that redirect and channel modern ocean circulation meant that deep water could circulate in more direct and unobstructed pathways, and the timescales of deep ocean turnover may have been different from those of the modern ocean. These differences in ocean circulation had effects on climate, on the distribution of nutrients in the ocean, and on the patterns of biological productivity that shaped the recovery of marine ecosystems through the Triassic. The Tethys Sea, the shallow tropical seaway that separated the northern and southern portions of Pangaea, was the most biologically productive marine environment of the Triassic. Protected from the full force of Panthalassic waves and currents by the surrounding land masses, the Tethys provided relatively stable, warm, shallow conditions that were ideal for the recovery and diversification of marine life. The reef-building communities of the Tethys were among the first to recover after the Permian extinction, and the marine reptile faunas that would characterize the Triassic Oceans first diversified in Tethyan environments before spreading into the open Panthalassic. There is a particular quality to a world in the early stages of recovery. It does not look like abundance. It looks like the beginning of abundance, which is subtly but importantly different. You can see the structure of it, the way a framework looks before the building is finished, all the essential supports in place but the walls not yet filled in, the spaces between things still more present than the things themselves. The Middle Triassic, roughly 247 to 237 million years ago, was a world in this state of becoming. The worst of the post-extinction heat had moderated. The periodic anoxic events that had been disrupting marine recovery throughout the early Triassic were becoming less frequent. Rainfall patterns were stabilizing into something approaching predictable seasonal cycles. The ecological landscape, stripped nearly bare by the Great Dying, was open in the way that only devastated landscapes can be, full of empty niches waiting to be filled, full of resources with no one yet competing for them. Opportunity, in evolutionary terms, is not a gentle thing. It is a pressure as powerful as any threat, driving populations to expand and diversify and experiment. The species that survived the Great Dying and their descendants were responding to this pressure with everything they had. Mutation rates were not higher than usual, but the survivors of natural selection were different ones than in more competitive times. In a world full of empty niches, the premium was on novelty. The slightly different body plan, the slightly expanded dietary range, the slightly more efficient locomotion. These small advantages could now translate into enormous reproductive success in ways they never could when every niche was already occupied by a well-adapted specialist. On land, the most prominent large animals of the Middle Triassic were the Dicynodonts and their relatives. Dicynodonts were a remarkable group, among the handful of synapsid lineages that had survived the Great Dying, and their survival had been a close thing. In the early Triassic they had been reduced to a few species in a few regions. But they were tough, generalist herbivores with a flexible diet and a robust physiology, and as conditions improved through the Middle Triassic they began to recover and diversify. Picture a Dicynodont. It is roughly the size of a large dog or in some species a small cow. Its body is barrel-shaped, built for processing large quantities of low-quality plant material in a digestive system that has to work hard to extract nutrition from the tough ferns and early conifers that constitute most of its diet. Its head is disproportionately large, heavy-skulled, with a toothless beak made of keratin at the front, like a turtle's, and in many species a pair of tusks near the jaw joint that are used for digging up roots and rhizomes. It moves with a kind of lumbering efficiency, its limbs not fully upright but also not fully sprawling, a posture somewhere between the two that is serviceable across a wide range of terrain types. Its skin is probably rough and relatively dry. It may have had simple scales or a leathery hide. Whether it had any hair or hair-like structures is unknown, though some of its synapsid relatives almost certainly did. It is not a graceful animal but it is an effective one, and in the Middle Triassic it is one of the most successful land animals on the planet. The Dicynodonts did not evolve in isolation. Around them, the Archosaur radiation was gathering momentum. The Archosaurs, that broad evolutionary grouping that would eventually produce dinosaurs, crocodilians, and pterosaurs, were diversifying rapidly through the Middle Triassic, trying out body plans and ecological strategies with the exploratory enthusiasm of a group that has suddenly discovered it has room to move. Some archosaur lineages were pursuing large predator strategies. The Rawasuchians, sometimes called Rawasuchids, were among the most successful, developing body plans that superficially resembled large theropod dinosaurs. Upright or semi-upright posture, powerful jaws, serrated teeth, long legs built for running down prey. Some Rawasuchians reached lengths of 5 or 6 meters and were undoubtedly the apex predators of the Middle Triassic terrestrial ecosystem. They were impressive animals, successful and widespread, and for much of the Middle and Late Triassic they held the top positions in their food chains. Other archosaur lineages were exploring herbivory. The Atosaur, armored archosaurs that looked something like armadillos scaled up to the size of a crocodile, were widespread and diverse, their broad flat teeth and rooting snouts suggesting a diet of roots, tubers and tough vegetation. They were heavily armored, covered in bony plates called osteoderms that formed a protective shell over their backs and sides. This armor probably served multiple purposes, protection from predators certainly, but possibly also thermoregulation, the dark bony plates absorbing heat from the sun in the cool mornings and evening and helping to maintain body temperature. There were also archosaurs that were exploring semi-aquatic lifestyles. The phytosaurs, which looked remarkably similar to modern crocodilians despite being only distantly related to them, had elongated snouts packed with teeth, heavy armor, and body plans optimized for lurking in rivers and coastal waterways and ambushing prey that came to drink. They were so similar to modern crocodiles that for a long time paleontologists assumed they were ancestral to them. They were not. The resemblance was convergent evolution, two unrelated lineages independently discovering that the long snout, armored, aquatic ambush predator body plan is an effective one. In the oceans the recovery was also accelerating. The most visible sign of this recovery was the diversification of marine reptiles. Several lineages of reptiles had taken to the sea in the Triassic, independently on multiple occasions, a pattern that suggests the marine environment was full of opportunity for animals that could adapt to it. The ichthyosaurs, already present in the early Triassic as fish-shaped swimmers, were diversifying through the Middle Triassic into an impressive variety of body sizes and ecological roles. Some were small and fast, chasing fish and cephalopods in open water. Others were becoming genuinely large, approaching or exceeding 10 meters in length, the first really big predators to appear in the post-extinction oceans. Alongside the ichthyosaurs, the nothosaurs were developing a semi-aquatic lifestyle that would eventually lead, through their descendants, to the fully aquatic plesiosaurs of the Jurassic and Cretaceous. Nothosaurs were long-necked, seal-like animals, equally comfortable on land and in the water, catching fish and squid with interlocking teeth designed to trap slippery prey. They ranged in size from small, otter-sized forms to genuinely large animals several meters long. Their coastal and near-shore habitat made them common inhabitants of the shallow tethys margins, and their fossils are among the most commonly encountered of Triassic marine vertebrates. The recovery of reef-building organisms was another milestone of the Middle Triassic. The sponge-dominated reefs that began to develop in the clearer, warmer waters of the Tethys Shelf were not the coral reefs we know today, those would come later, built by organisms that had not yet evolved. But they performed similar ecological functions, providing complex three-dimensional structures that sheltered dozens of other species, concentrating biological activity in limited areas, creating the kind of rich, layered habitat that supports high biodiversity. In the skies, the Middle Triassic was still relatively empty. The pterosaurs had not yet appeared, or if they had not yet left fossil evidence that we have found. The skies were inhabited by insects, increasingly diverse ones, and by the occasional archosaur that had evolved the ability to glide, but powered flight invertebrates was still millions of years in the future. The air was open in a way that the land and the sea were increasingly not. And on the forest floor, in the shadows beneath the early conifers and cycads, in the leaf litter and the loose soil along stream banks, something small was moving that would prove, in the long run, to be among the most consequential developments of the entire Triassic. The cynodonts, advanced mammal-like reptiles that were the most derived of the surviving synapsid lineages, were evolving with a speed and creativity that belied their small size and apparently modest position in the ecosystem. Cynodonts had survived the Great Dying in small numbers. Through the early Triassic they had been uncommon, overshadowed by the more abundant dicynodonts. But through the Middle Triassic they were diversifying steadily, exploring a range of body sizes and dietary strategies. Some were still small insectivores, delicate-boned creatures no larger than a mouse that hunted insects and small invertebrates in the dense leaf litter. Others had grown larger and developed crushing teeth suitable for processing roots and seeds. A few had become specialized to eat other vertebrates. What made the cynodonts particularly interesting, and what would eventually make their descendants, the true mammals, so important, was a suite of physiological and behavioral traits that they were developing during this period. Their teeth were differentiating, front teeth for biting, cheek teeth for processing, a pattern that allowed much more efficient extraction of nutrition from food. Their jawbones were simplifying, with some of the original reptilian jaw bones migrating toward the ear region, eventually to become the tiny bones of the mammalian middle ear. Their metabolisms were probably elevated compared to typical reptiles, their bodies running warmer, their activity less dependent on external temperature. None of this was finished in the Middle Triassic. None of it was obvious. The cynodonts of this period still looked more like reptiles than mammals to a casual observer, and in most ecological contexts they were playing second fiddle to the larger, more conspicuous archosaurs. But the direction was set. The architecture was being constructed. And in the quiet spaces beneath the canopy, in the darkness of burrows and the shelter of root systems, the future of warm-blooded, large-brained, live-bearing vertebrate life on Earth was being very quietly assembled. The world of the Middle Triassic was busy in a way the Early Triassic had not been. There were more species, more ecological interactions, more complexity in the webs of dependency that connected organisms to each other. It was not yet the lush, diverse world of the Late Triassic or the Jurassic, but it was moving in that direction with purpose. The empty spaces were filling, slowly but with growing momentum. The architecture of a new age was taking shape. The process of ecological recovery was not merely a matter of species filling empty niches. It was also a process of relationship building, of the slow establishment of the networks of dependency and interaction that make an ecosystem function as a coherent system rather than a random collection of organisms. The plants needed fungi to help their roots absorb nutrients. The animals needed specific food plants that were themselves dependent on specific soil conditions. The decomposers needed the right temperature and moisture to function efficiently. All of these relationships had been disrupted by the Great Dying, and rebuilding them was a project that took millions of years. The mycorrhizal fungi, those ancient partners of land plants whose networks in the soil connect root systems across enormous distances, were among the most important rebuilders of the terrestrial ecosystem. Modern research has shown that healthy forests are maintained partly through underground fungal networks that allow trees to exchange nutrients and even chemical signals with each other. These networks were present in the Triassic, and their gradual re-establishment as plant communities recovered was a crucial part of the process that allowed forests to develop the complexity and productivity that they eventually achieved. The rivers and streams of the Middle Triassic were beginning to develop something like a characteristic character. Not the uniformity of water running over bare rock, which had been the dominant style of the early Triassic, but the more complex hydrological behavior of water moving through a landscape partially clothed in vegetation. Plant roots stabilized stream banks, reducing erosion and allowing rivers to develop more sinuous courses. Leaf litter fell into streams and became food for aquatic invertebrates. The shade of streamside vegetation reduced water temperature and increased oxygen content. Slowly, step by step, the rivers were becoming ecosystems rather than simply physical processes. The therapsids, the broader group to which the cynodonts and dicynodonts both belonged, had been the dominant vertebrates of the late Permian world. Their nearly complete elimination in the Great Dying had left an ecological landscape that was simpler and harder than anything the planet had seen in over 100 million years. Their partial recovery through the Triassic was not a restoration of the Permian world but something new, shaped by the pressures of the post-extinction environment in ways that would give rise to entirely new evolutionary trajectories. The Middle Triassic was also the time when true turtles first appeared in the fossil record. The earliest turtle relatives, animals with broadening ribs that foreshadow the later full shell, come from Middle Triassic deposits in China and Germany. Their appearance at this point in geological history rather than at any other, is probably not coincidental. The expanding coastal and freshwater habitats of the recovering Triassic world provided the ecological context in which a bottom-dwelling, slow-moving animal with heavy protective armor might find sufficient food and sufficient refuge from predators to make the enormous developmental costs of the shell worthwhile. Everything in the Middle Triassic ecology was, in one way or another, shaped by the memory of catastrophe. Not the memory of individual organisms, which have no such memory, but the memory of natural selection, the accumulated record of which traits had helped organisms survive the terrible pressures of the Permian-Triassic crisis and which had not. The survivors were not merely lucky. They carried in their bodies the marks of the selection process that had tested every lineage and found most of them wanting. The traits they carried were the traits that had worked, and they carried them forward into a world that would test them in new ways. The nervous systems of Middle Triassic vertebrates were more sophisticated than those of their early Triassic predecessors in ways that went beyond simple brain size increase. The processing of sensory information, particularly visual information, was improving in multiple lineages simultaneously, driven by the increasing ecological complexity of the recovering world. More species meant more potential predators, more potential prey, more potential competitors, and the ability to quickly identify and categorize the moving shapes in the visual field was becoming more valuable. The improvement of visual processing in archosaurs in particular may have been one of the factors that contributed to their competitive success over more poorly sighted competitors. Social behavior, though difficult to document from fossil evidence alone, was probably developing complexity in Middle Triassic vertebrate communities. Modern crocodilians, the closest living relatives of archosaurs, show a range of social behaviors including vocalizations, territorial displays and parental care, and there is no reason to think that their Triassic relatives were entirely solitary. The fossil record occasionally preserves evidence of social groupings in Triassic vertebrates, and the ecological incentives for social behavior, collective vigilance against predators, cooperative hunting, group thermoregulation, were present in the Middle Triassic just as they are in modern ecosystems. The first generations of Triassic life to establish themselves in the recovered world were not passive inheritors of a gift. They were active participants in a reconstruction, their metabolisms processing the accumulated organic matter of the mass extinction, their movements dispersing seeds and spores into newly available territories, their predatory activities maintaining the selective pressure that kept prey populations robust and adaptable. Life is not simply a passenger on the geological and chemical systems of the planet. It is a co-author of those systems, shaping the atmosphere and the soils and the ocean chemistry even as those systems shape the conditions within which life must operate. Come with me to the water. The land has told us much, but the sea has its own stories, and in the Triassic those stories are extraordinary. Walk with me down to the edge of the Tethys, the great inland sea that cuts across the middle of Pangaea, warm and shallow and lit from above by a sun that penetrates its green water to considerable depth. The shore here is not sandy. It is a mix of limestone rubble and fine carbonate sediment, pale and warm underfoot, and the water that laps against it is the color of old glass, clear enough that you can see the bottom at 10 meters 20, the pale seafloor dimming to blue-gray and then to darkness as the shelf drops away. The smell is the smell of a warm, productive ocean, rich with the organic compounds produced by billions of photosynthetic organisms, touched with the slight sulfurous edge of biological decomposition that is always present in shallow marine environments. It is not unpleasant. It is the smell of life at work, of energy moving through systems, of matter being assembled and disassembled in the great cycling of organic chemistry that defines all marine ecosystems. The Middle and Late Triassic oceans were in the process of rebuilding something remarkable. The Great Dying had stripped them almost bare. The diverse and complex marine ecosystems of the Permian, built over hundreds of millions of years of evolutionary refinement, had collapsed with devastating completeness. What remained were the simplest, most opportunistic organisms, and even they had been reduced in diversity and abundance. But two things that extinction cannot permanently suppress are time and selection pressure, and the Triassic oceans had both in abundance. Time because recovery always takes time, and the Triassic had tens of millions of years to work with. Selection pressure because the empty niches of the post-extinction ocean represented enormous evolutionary opportunity, and the survivors were responding to it. The ichthyosaurs were the most spectacular of the Triassic marine recovery stories. These were not the graceful, dolphin-shaped creatures that most people picture when they hear the word ichthyosaur. Those would come later, in the Jurassic and Cretaceous. The Triassic ichthyosaurs were a more diverse and experimental lot, their body plans still in the process of being refined by natural selection, trying out different solutions to the challenges of large-body marine predation. In the Middle Triassic, ichthyosaurs ranged from small eel-like forms that probably lurked in coastal shallows to genuinely enormous animals. The largest, known from specimens found in what is now Nevada and British Columbia, were among the biggest animals that had ever lived up to that point in Earth's history. Shanosaurus popularis, for example, reached lengths of 15 meters, comparable to a large sperm whale. Its sheer size would have been staggering in an era when the largest land animals were still modest in comparison. What did these great ichthyosaurs eat? The question is more complex than it might seem. A 15-meter predator needs an enormous amount of food, and the Triassic oceans, still recovering from the Great Dying, did not have the dense populations of large fish and cephalopods that would later sustain similarly large marine predators. Some researchers have proposed that the largest Triassic ichthyosaurs may have been filter feeders, like modern whale sharks or baleen whales, straining enormous quantities of small organisms from the water. Others argue they were active predators, pursuing large cephalopods and other sizable prey. The truth may have varied between species and life stages. The ammonoids were among the great success stories of Triassic ocean recovery. These coiled cephalopods, relatives of the modern nautilus and the extinct relatives of squid and octopus, had been nearly annihilated by the Great Dying. A single family, the Hedenstroemidae, appears to have survived the extinction, and from that narrow bottleneck the entire subsequent ammonoid diversity of the Triassic exploded. This is evolution at its most dramatic, a single surviving lineage radiating into dozens, then hundreds of species within a few million years, filling the empty ecological space with a profligacy that seems almost reckless. Ammonoids are valuable to scientists not just as evolutionary curiosities but as markers. Because they evolved so rapidly and went extinct so completely at various points in the geological record, their changing shell forms can be used to date rock layers with remarkable precision. Triassic rocks worldwide can be matched and dated by their ammonoid assemblages, and this precise dating has allowed paleontologists to reconstruct the timeline of Triassic events with a resolution that would be impossible with many other fossil groups. The bivalves were another group that found the Triassic oceans to their liking. Clams and their relatives had survived the Great Dying in reasonable shape and were diversifying through the Triassic into a wide range of ecological roles. Some were burrowers, living in the sediment. Others attached themselves to hard surfaces. A few evolved the ability to swim by clapping their shells together and propelling themselves through the water. The bivalves were not glamorous animals, but they were effective ones, and their diversity and abundance made them foundational components of Triassic marine food webs. The nothosaurs were occupying the shallow coastal zones with increasing success through the Middle Triassic. These long-necked, fish-eating reptiles were not committed to fully aquatic existence in the way the ichthyosaurs were. They still retained functional limbs that could support their weight on land, and they likely hauled out on beaches and rocky shores to rest and breed, much as modern seals do. Their fossils are found not just in marine deposits but in coastal and estuarine sediments, evidence of animals comfortable in the transition zone between land and sea. The placodonts were another fascinating group of Triassic marine reptiles, though they occupied a very different ecological niche from the ichthyosaurs or nothosaurs. Placodonts were specialized shellfish eaters, their jaws and teeth modified into crushing platforms that could crack open hard-shelled mollusks with ease. Some placodonts developed heavy armor, rows of bony plates along their backs and tails that gave them a superficial resemblance to modern sea turtles, another example of convergent evolution leading distantly related animals to similar solutions for similar problems. The reefs were growing. Slowly, tentatively but unmistakably, the shallow carbonate shelves of the Tethys Sea were being colonized by reef-building organisms. The early Triassic reefs were small and simple, dominated by sponges and microbes rather than the corals that would later take over this ecological role. But through the Middle Triassic, the reefs were becoming more complex, more three-dimensional, more capable of supporting the diverse communities of associated organisms that make reef ecosystems so extraordinarily productive. The diversity of reef-associated fish was increasing in parallel. Fish had survived the Great Dying better than many marine groups, and through the Triassic they were diversifying into the range of ecological roles that would eventually make them the dominant vertebrates in every aquatic habitat on Earth. Ray-finned fish, the actinopterygians, which today include the vast majority of all fish species from tuna to goldfish, were undergoing a significant diversification in the Triassic, their bodies and feeding apparatus becoming increasingly specialized for different modes of life. Sharks were present throughout the Triassic, as they had been through every major extinction event, their resilience a function of their simple but highly effective body plan and their wide ecological tolerance. Triassic sharks were diverse in form, from small, slim species that probably hunted invertebrates in shallow water to larger, more robust forms that were genuine predators. They occupied coastal zones, open ocean, and deep water, their cartilaginous skeletons preserving poorly in the fossil record but leaving enough evidence through their teeth and scales to tell us of their continued presence and diversity. The open ocean, the Panthalassic, the vast world ocean that covered 2/3 of the planet's surface, was harder to read from the fossil record. Deep ocean sediments from this period are almost entirely subducted, consumed by the movement of tectonic plates back into the mantle over the subsequent 250 million years. What we know of the open ocean Triassic comes largely from organisms that found their way into shallow water environments and were preserved there, and from the occasional windows that uplifted marine sediments provide. What we can say is that the open ocean was not empty. The phytoplankton that formed the base of the marine food web had recovered quickly after the Great Dying, as they always do, their simple biology and rapid reproduction making them resilient to even catastrophic disruptions. Zooplankton followed the phytoplankton, and fish and marine reptiles followed the zooplankton, and by the Middle Triassic the basic structure of a complex open ocean ecosystem was present, even if its details differed substantially from the oceans we know today. Standing at the edge of the Tethys and looking out across its warm, productive surface, you are looking at a world in the process of reassembling one of the most complex systems that nature produces. The work is far from finished. There are still enormous empty spaces in the ecological architecture, still niches with no occupants, still evolutionary experiments still in progress. But the direction is clear and the pace is quickening, and something about the quality of the light on the water, the way it fragments into 1,000 mobile points of brightness, suggests that the sea is not mourning what it lost. It is building what comes next. The ammonoids that swam in Triassic seas had shells that ranged from simple, tightly coiled spirals to elaborate, sculptured forms with prominent ribs and nodes on their surfaces. These sculptures were not random. They appear to have served functions related to the ammonoid's ecology, perhaps providing camouflage through a texture that matched the seafloor, perhaps providing hydrodynamic control in the water column, perhaps serving a role in species recognition among animals that may have had complex social behaviors. The variety of shell forms represents the diversity of ecological strategies being tested by a group that had survived a catastrophic bottleneck and was now exploring the possibilities of its recovered diversity. The benthic communities of the Middle Triassic seafloor were in the process of rebuilding the complex, layered architecture that characterizes healthy marine bottom environments. Burrowing animals, animals that live on the surface of the sediment, and animals that attach to hard surfaces all contribute to this architecture in different ways, and the process of rebuilding required that all three groups recover and diversify together. The burrowing animals aerated the sediment and mixed organic matter down into it. The surface dwellers processed organic material and created new substrate for attachment organisms. The attachment organisms, sponges and early relatives of later reef builders, created the physical complexity that sheltered dozens of other species. Fish diversity in the Triassic oceans was growing steadily, with ray-finned fish in particular undergoing significant diversification. The early Triassic had been a difficult time for fish, as it had been for most marine organisms, but the recovering ecosystems of the Middle Triassic provided expanding opportunities for the various fish lineages that had survived. Some were becoming more specialized for particular food sources, developing teeth adapted for crushing shellfish or grinding plant material. Others were becoming more generalist, expanding their dietary flexibility in ways that made them more resilient to future disruptions. The Tethys Sea was also host to a remarkable diversity of marine invertebrates that left no dramatic large fossils but that were essential components of the ecosystem. Foraminifera, tiny single-celled organisms that build elaborate calcium carbonate shells, were diversifying through the Triassic and developing the extraordinary variety of shell forms that makes them so useful to geologists for dating rock sequences. Ostracods, small crustaceans whose two-valved shells are preserved abundantly in many Triassic marine deposits, were also diversifying, their different species adapted to different water depths, temperatures and salinities. The interaction between the recovering marine biosphere and the physical chemistry of the ocean was a two-way relationship. As marine organisms diversified and increased in abundance, they altered the chemistry of the water around them, drawing down dissolved carbon dioxide through photosynthesis and carbonate shell production, releasing oxygen, processing nitrogen and phosphorus through their metabolisms. These biological processes gradually shifted the ocean chemistry toward the conditions that would support even greater diversity, a positive feedback loop that accelerated recovery once it got properly started. The coastlines of Pangaea where rivers met the sea were zones of particular biological importance. The mixing of fresh and salt water, the concentration of nutrients from terrestrial runoff, the shallow water and soft sediment of estuaries and deltas, these conditions supported communities that were different from both purely marine and purely freshwater environments. The brackish water specialists that developed in these transitional zones were often unique, adapted to conditions that occurred nowhere else, and their evolution added another layer of diversity to the recovering world. The chemical signals preserved in Triassic marine sediments include biomarkers, specific organic molecules produced by particular types of organisms that can survive for hundreds of millions of years in the right depositional conditions. Biomarkers from Triassic marine sediments have revealed the presence of organisms that left no body fossils, including specific groups of bacteria and algae whose chemical signatures are preserved even when their cells are long gone. These invisible organisms were important components of the marine ecosystem, and their chemical record fills in aspects of the Triassic Ocean's biology that the visible fossil record misses. The depth zonation of Triassic marine communities was becoming more complex through the period as the oxygen content of deeper water improved and as the diversity of organisms adapted to different depths increased. The shallowest zones, lit by sunlight and rich in photosynthetically produced oxygen, supported the most diverse communities. The middle depths, below the photic zone but above the fully anoxic deep water, supported specialized communities adapted to low oxygen conditions. The deepest waters were still largely lifeless in the early and middle Triassic, the legacy of the anoxic conditions that had prevailed during the extinction, but were gradually being colonized as conditions improved. The chemistry of Triassic seawater was not identical to that of modern oceans. The long-term cycling of elements between the ocean and the seafloor, between ocean water and continental rocks through weathering, maintains the composition of seawater within a range that varies on geological time scales. The elevated carbon dioxide levels of the Triassic, combined with the different rates of weathering and volcanic input that characterized the period, would have produced seawater with subtly different calcium, magnesium and carbonate ion concentrations than modern seawater. These differences affected the calcification strategies available to marine organisms, influencing which groups could build shells and skeletons efficiently and which found the chemistry of Triassic seawater more challenging. The paleobiogeography of Triassic marine faunas reflects the connectivity provided by the Tethys Sea and the Panthalassic Ocean in complex ways. Some species were cosmopolitan, found in marine deposits from what is now Europe through Asia to North America, suggesting that they could disperse effectively across ocean distances and that no significant barriers prevented their spread through the Triassic marine world. Others were more restricted in their distribution, confined to particular regions or ocean basins, suggesting either that they could not disperse effectively or that they were specialists adapted to conditions found only in particular environments. Walk into the forest. It is not yet the forest it will become, not the towering conifer cathedral of the Jurassic, not the flowering bird-filled canopy of the Cretaceous. It is something older, stranger, shaped by constraints and opportunities that no longer exist in the world we know. But it is a forest, and standing inside it, in the green light filtered through unfamiliar leaves, with the smell of resin and wet earth and the particular sweetness of plant metabolism all around you, something about it is deeply, wordlessly familiar. The canopy above you is dominated by conifers. Not quite like modern conifers, though their relationship to living families is clear if you look carefully. Their needles are arranged differently than those of a modern pine, their cones have a structure that combines familiar elements in unfamiliar proportions. They are large trees, some of them, their trunks reaching diameters of a meter or more, their branches spreading in the patient horizontal architecture that all conifers favor, capturing as much sunlight as possible across their flat plains. The understory is filled with cycads. These ancient plants, which survive today as living fossils in tropical and subtropical regions, were in the Triassic at the peak of their diversity and ecological importance. Cycads are not trees exactly, though they grow tall enough to function as trees. They are more closely related to pine trees than to palms. Despite their superficial resemblance to palms, their stiff fronds radiating from a central trunk in a symmetrical crown. They produce seeds in enormous cones at the top of their trunks, some of the most elaborate seed-producing structures in the plant kingdom. Cycads were common in Triassic forests for good reasons. They are remarkably tolerant of drought and heat, capable of storing water in their thick trunks and reducing water loss through their waxy, stiff fronds. They can fix nitrogen through symbiotic relationships with cyanobacteria in their root systems, giving them a nutritional independence that makes them less dependent on fertile soil than most plants. In the difficult, variable climate of Triassic Pangaea, these were significant advantages. The ground beneath your feet in this forest is soft with the accumulated debris of seasons, needles and frond fragments and the decayed remnants of fallen branches, all slowly being processed by the fungi and bacteria that are the invisible but essential workforce of every terrestrial ecosystem. The soil here is richer than the bare mineral substrate of the interior plains, Enriched by thousands of years of organic accumulation, its structure improved by the roots of the plants above and the activities of the invertebrates below. Ferns occupy every available patch of ground between the larger plants. Ferns are ancient, predating the seed plants by tens of millions of years, and they have been adapting to forest understories for long enough that they have become very good at it. Some are small and delicate, their fronds no larger than your hand, collecting the scattered photons that make it through the canopy in deeply shaded spots. Others are robust, waist-high, with fronds that spread wide enough to capture significant light even in partially shaded conditions. Tree ferns stand taller, some of them reaching several meters, their crowns of arching fronds creating a middle layer between the ground cover and the canopy trees. Tree ferns are an ancient growth form, dating back to the Carboniferous coal forests, and they survived the Great Dying with better success than many plant groups. In the Triassic, particularly in moister regions and along watercourses where soil moisture remained available through the dry season, tree ferns were important components of the forest structure. The Dichroidium flora deserves special mention because it dominated the southern reaches of Pangaea throughout much of the Triassic. Dichroidium itself was a seed fern, a plant group that is now entirely extinct, whose leaves forked repeatedly in a distinctive pattern that makes them immediately recognizable in the fossil record. Seed ferns were not ferns in the modern sense and not angiosperms, they occupied an intermediate position in plant evolution, producing seeds like conifers but lacking the woody trunks and specialized seed cones of conifers. Dichroidium forests covered much of what is now Antarctica, Australia, South America, Africa, and India during the Triassic, those landmasses that collectively formed the southern supercontinent Gondwana before the final assembly of Pangaea. The distribution of Dichroidium fossils was, in fact, one of the earliest and most compelling lines of evidence for continental drift, since the same plant species occurring on continents now separated by thousands of kilometers of ocean made no sense unless those continents had once been joined. In the moister regions of Pangaea, particularly along the coasts and in the valleys where river systems maintained year-round water availability, the forest was genuinely lush. The Triassic had moisture-demanding plant communities that supported dense canopies and rich understories, forests that would not have looked entirely out of place in a modern subtropical setting, though the specific plants would have been entirely unfamiliar. The interactions between these plants and the animals that depended on them were complex and co-evolving in real time. Herbivores were the primary drivers of plant evolution during this period, their preferences and digestive abilities creating selection pressure for defense. Plants evolved mechanical defenses, thick cuticles, tough fibrous tissues that were difficult to chew. Chemical defenses, resins and tannins and alkaloids that made leaves unpalatable or toxic. Physical architecture, positioning their most nutritious and vulnerable tissues in locations difficult for herbivores to reach. The conifers in particular were notable chemists. Their resin systems, networks of canals running through wood and bark and needles, produced a complex mixture of terpenes and other organic compounds that functioned as both anti-herbivore deterrence and antifungal protection. This resin, when it flowed from wounds in the bark and hardened on exposure to air, preserved anything that became trapped in it with remarkable fidelity. Insects, plant fragments, sometimes small vertebrates, all captured in the moment of their misfortune and held there for hundreds of millions of years, waiting for a scientist to find them and peer through the amber window into the Triassic world. Horsetails, those primitive vascular plants with hollow segmented stems and tiny scale-like leaves, were particularly abundant along stream banks and in wetland margins. Modern horsetails are small, typically less than a meter tall, but their Triassic relatives were in some cases much larger, reaching heights of 5 or 6 meters along the richest waterways. Their silica-reinforced stems made them resistant to herbivory, and their ability to colonize disturbed, wet ground made them first comers to any newly flooded or eroded area. Ginkgos were beginning their long Triassic diversification. The ginkgo, that extraordinary tree known as a living fossil because the species Ginkgo biloba alive today is virtually identical to Triassic forms, was in the Triassic represented by many more species than the single survivor we know today. Ginkgo fossils, with their distinctive fan-shaped leaves, appear at sites across the northern hemisphere throughout the Triassic, their presence telling us of a group of plants that was not yet the rare relict it would become, but a diverse and widespread component of temperate and subtropical forest ecosystems. The role of plants in the broader ecological story of the Triassic cannot be overstated. Plants are the foundation of every terrestrial food web, the primary captors of solar energy and the primary producers of the organic matter that supports all other life. The rate at which the plant communities of the Triassic recovered and diversified directly determined the rate at which herbivore communities could expand, and the expansion of herbivore communities directly determined the opportunities available for carnivores, and the success of all of these groups together determined the pace at which the broader ecosystem recovered its complexity and productivity. The forests of the Triassic were also significant as carbon stores. Forests lock up enormous quantities of carbon in their wood, their roots, and their soil organic matter, and the recovery and expansion of forest cover through the Middle and Late Triassic played an important role in drawing down the atmospheric carbon dioxide that had been elevated by the volcanic catastrophe at the Permian-Triassic boundary. This drawdown contributed to the gradual cooling of global temperatures through the Triassic, creating the more moderate conditions that allowed animal diversity to increase. There is something meditative about a forest, any forest but especially this one. The light comes through in pieces, falling on the forest floor in shifting shapes that move as the canopy moves in the wind. The sounds are gentle, the rustle of fronds, the occasional creak of a branch, the drip of water from a leaf after the morning's brief rain. You are very small here, in the middle of a living system whose complexity exceeds any complete description, a system that is still assembling itself, still finding its shape, still learning what it can become. The forest does not know it is in the Triassic. It does not know that it is early, that the great flowering of life that is coming would make this seem like a rehearsal. It is simply doing what forests do, reaching toward the light, cycling nutrients through the soil, sheltering the small creatures that move through its shadows. It is patient the way only things that do not know time can be patient. And in that patience, it is building, quietly and without drama, the foundation of a world. The spores and pollen that fell from the Triassic forests and were preserved in the sediment below them tell a detailed story of the plant communities of the time. Palynology, the study of fossil pollen, has been one of the most productive approaches to understanding Triassic plant communities because pollen is abundant, widely dispersed, and well preserved in many sedimentary environments. The pollen record from the Triassic shows the gradual replacement of typical Permian plant assemblages with new combinations, the appearance of new plant groups, and the eventual establishment of the conifer-dominated forests that would persist through the rest of the Mesozoic. The relationship between plants and the insects that visited their reproductive structures was developing through the Triassic in ways that would eventually produce the extraordinary diversity of insect-plant interactions that defines the modern world. Many Triassic plants relied on wind pollination, releasing vast quantities of pollen into the air and relying on chance for its delivery. But some of the more derived Triassic plants were beginning to develop relationships with specific insect visitors, producing structures that attracted insects and rewarded them with food while ensuring that pollen was transferred from plant to plant. The soil ecosystem of Triassic forests was developing its own complexity. The thin soils of the early Triassic, lacking the biological infrastructure of a mature soil community, were being transformed by the accumulated input of organic matter from the growing plant communities above. Earthworm-like organisms were processing organic material and mixing it with mineral sediment. Mites and springtails, tiny arthropods that today are among the most abundant animals in any forest soil, were diversifying in the Triassic and becoming important drivers of decomposition and nutrient cycling. The invisible community below the forest floor was in many ways as important to the functioning of the ecosystem as the visible community above it. The chemistry of the Triassic atmosphere was being influenced by the recovering forests in ways that would have long-term effects on global climate. Photosynthesis removes carbon dioxide from the atmosphere and fixes it in organic carbon, and the expansion of forest cover through the Triassic contributed to the gradual drawdown of the elevated CO2 levels that had been a legacy of the Permian volcanic catastrophe. The burial of organic carbon in the sediments below Triassic swamps and lakes added another carbon sink, locking away material that would otherwise have eventually decomposed and returned its carbon to the atmosphere. Water was the organizing principle of Triassic plant communities. Where water was reliably available, complex multi-layered forests could develop. Where water was seasonal, plants with drought tolerance dominated. Where water was scarce, only the most specialized desert-adapted plants could survive. The detailed pattern of plant community distribution across the Triassic landscape was essentially a map of water availability, and the changes in that pattern over the course of the period tracked the changing climate with a precision that few other lines of evidence can match. The most ancient living trees alive in the world today are giant sequoias and bristlecone pines, organisms that have been alive for thousands of years. The forests of the Triassic, by contrast, are accessible to us only through their fossil remains, the compressed and mineralized wood and leaves and spores that are all that remain of organisms that were living and breathing when the dinosaurs were new. To walk through a Triassic forest would be to walk through a world that is, in its broad outlines, comprehensible to a botanically informed modern observer but filled with an alien specificity that no amount of fossil study can fully reconstruct. The smell of the resin, the texture of the bark, the sound of wind in unfamiliar needles, these are gone, preserved only in the carbon-rich rock that is all the trees have become. The seasonal rhythm of the Triassic forest was written in the wood of its trees in a way that persists to the present in the fossil record. Tree rings, the annual growth layers visible in cross-sections of fossil wood, record the alternation of fast growth during the wet season and slow or no growth during the dry season. The width of individual rings varies with the quality of conditions in each particular year, a climatic record spanning the lifetime of each individual tree. Fossil wood from Triassic sites in Antarctica and high-latitude Europe shows clear tree rings even though those regions were closer to the poles than today, evidence that Triassic seasonality, driven by the astronomical cycles of Earth's orbit and axial tilt, was felt even in the relatively mild high latitudes. The relationship between Triassic plants and the fungi that helped them access soil nutrients was a partnership of extraordinary antiquity. Mycorrhizal associations between plants and fungi date back to the earliest colonization of land by plants, hundreds of millions of years before the Triassic, and the recovery of these associations after the Permian-Triassic extinction was one of the crucial steps in the recovery of productive terrestrial ecosystems. The fungi, which lack the rigid cell walls that might preserve them as body fossils, are largely invisible in the fossil record, but their importance is inferred from the ubiquity of mycorrhizal associations in every living plant community and from the occasional preservation of fungal hyphae in fossil wood and soil. Look up. The canopy of the conifer forest filters the late afternoon light into something golden, and against that gold, something moves. It is small, perhaps the size of a crow, and it moves with a confidence that suggests long familiarity with this dimension of space. It banks around the trunk of a large tree, drops briefly, rises again on a thermal rising from the sun-warmed rock of a nearby outcrop, and then is gone, moving away through the forest into the open sky beyond the treeline. You have just seen, if only briefly, a pterosaur. And this is extraordinary because nothing like it has ever flown before. The origin of pterosaurs is one of the enduring mysteries of paleontology. Unlike birds, which have a beautifully complete fossil record tracing their evolution from small feathered dinosaurs, or bats, whose earliest fossil ancestors are already fully formed flyers, pterosaurs appear in the fossil record at or near the beginning of the late Triassic essentially complete, already capable of powered flight, with no obvious transitional fossils connecting them to their non-flying archosaur ancestors. The oldest pterosaur fossils we know of come from the late Triassic, roughly 228 to 210 million years ago, from sites in Italy, Greenland, and North America. These earliest pterosaurs, animals like Eudomorphodon and Patenosaurus, were already accomplished flyers. Their wings were fully developed membrane structures, their wing membranes supported by a dramatically elongated fourth finger that served as the primary wing spar, with the membrane extending back to attach to the hind limbs. Their bones were hollow and thin-walled, reducing weight. Their brains show enlargement of the regions associated with vision and balance, adaptations for the constant spatial calculation that flight demands. The fact that these early pterosaurs were already fully capable flyers when we first find them means that the evolution of flight in their lineage happened earlier, in a period from which we have not yet recovered fossil evidence. Some researchers believe pterosaur ancestors were small, tree-living archosaurs that evolved gliding ability first, then powered flight. Others argue for a ground-up origin, small cursorial animals that evolved wings as a running or leaping aid. The debate continues. What we can say with confidence is that the Triassic world provided exactly the conditions in which flight would have been powerfully advantageous. The forests were extensive and complex, providing both the updraft-generating canopy surfaces and the insect-rich environments that a flying insect hunter would need. The open coastal plains provided thermal currents rising from sun-heated rock. The Tethys Sea provided enormous potential feeding grounds for any animal that could reach it from a sufficient altitude. Eudomorphodon, one of the best-known early pterosaurs, has left us remarkably detailed fossils from northern Italy. From these we can see an animal with a wingspan of roughly 1 meter, its wings equipped with a flight membrane that appears to have been relatively stiff and efficient. Its teeth were remarkable, a mixture of long, fang-like front teeth for seizing prey and smaller, multicusp cheek teeth that suggest a varied diet. Stomach contents in some specimens show fish remains, suggesting these early pterosaurs were already exploiting the rich coastal and lake fisheries of the late Triassic. The tail of early pterosaurs was long, extending behind the body and usually equipped at its tip with a diamond-shaped membrane vein. This arrangement, a long stiff tail with a terminal stabilizer, is similar to the tails of early aircraft, and served a similar function, providing stability in flight and helping to control pitch and yaw. Later pterosaurs would reduce this long tail to a stub, making them more maneuverable if less stable, but the early forms retained this ancestral tail architecture. The wing membrane of pterosaurs was more complex than the membranes of modern bats, which are the best modern comparison. Bat wings are essentially stretched skin, relatively simple in structure. Pterosaur wing membranes contained a layer of reinforcing fibers, actinofibrils, whose precise nature and orientation varied between species and probably contributed significantly to the aerodynamic properties of the wing. The membrane also appears to have contained a network of blood vessels and possibly some degree of muscular control, allowing the pterosaur to subtly adjust the shape of its wing in ways that a simple skin membrane could not. The metabolism of pterosaurs is another question that has generated significant research and debate. Modern reptiles are generally ectothermic, relying on external heat sources to regulate their body temperature, which limits their activity levels in cool conditions. But pterosaurs, to fly effectively, would have needed to maintain high activity levels regardless of ambient temperature. The evidence from bone growth patterns and from skin impressions showing a covering of hair-like pycnofibers strongly suggests that pterosaurs were indeed endothermic, warm-blooded in the way that birds and mammals are, generating their own body heat and maintaining a constant elevated body temperature. This is significant beyond just flight capability. Endothermy is metabolically expensive, requiring much more food to maintain a given body size than ectothermy. But it also allows a much wider range of activity, greater responsiveness, more sophisticated nervous system operation, and the ability to remain active through the cool nights and mornings that would have grounded a cold-blooded flyer. The pterosaurs, if they were truly endothermic, were managing their energy budgets in fundamentally the same way that birds do today. The ecological impact of the pterosaurs on Triassic ecosystems was immediate and significant. They were the first vertebrates to access the aerial niche, and in doing so they opened up a new dimension of the ecosystem that had previously been available only to insects. Their ability to travel rapidly over large distances, cover the coast to inland forest transition in a matter of minutes, allowed them to exploit food resources over geographic ranges that were impossible for terrestrial animals. They were integrators, moving energy between different parts of the ecosystem in ways that nothing else could. The diversity of pterosaurs through the late Triassic expanded steadily as they moved into new ecological roles. Some species remained small, probably insectivorous, hunting over forests and open water. Others grew larger and shifted toward fish eating, developing longer jaws and forward-pointing teeth that were effective for snatching fish from the water surface. A few appear to have been primarily terrestrial foragers when not flying, their limb proportions suggesting they were equally comfortable walking as soaring. The pterosaurs also faced competitors in the air. Insects had been flying for 250 million years before the pterosaurs appeared, and by the Triassic they were enormously diverse and widespread. The early pterosaurs were pursuing large prey in most cases, fish and large insects, but they inevitably interacted with the insect communities they flew through. Some early pterosaur teeth are clearly adapted for catching large, tough-bodied insects, and the relationship between the diversification of flying insects and the diversification of pterosaurs was undoubtedly complex and reciprocal. There were also gliding reptiles in some Triassic habitats that occupied an adjacent niche without being true flyers. Queniosaurus and its relatives were lizard-like archosaurs that had evolved elongated ribs, capable of being spread outward from the body to create a gliding surface. These were not powered flyers, they could not sustain altitude without a thermal or rising air, but they could glide from tree to tree or from height to the forest floor with considerable control, escaping predators or accessing food sources that purely terrestrial animals could not reach. Watching the pterosaur bank and wheel against the golden sky, you are watching the moment when vertebrate life first fully committed to the air. Not the tentative gliding of the caniosaurs, not the insect-like aerial maneuvers of something without bones and blood, but the real thing, a creature of flesh and bone and warm blood, metabolically equipped for sustained powered flight, anatomically optimized for a life spent largely above the ground. The significance of this moment extends forward through time in ways that are difficult to fully appreciate. The pterosaurs themselves would persist for 160 million years, diversifying into forms ranging from sparrow size to the largest flying animals the planet has ever produced. They would be joined, eventually, by the birds, descendants of small feathered dinosaurs that would eventually displace them in most aerial niches. But the precedent was set here in the late Triassic, when the first pterosaur spread its membranous wings and discovered that the air was available. The sky above Pangaea was no longer empty. It had found its first true inhabitants, and they were learning, with every thermal and every fish-snatching dive, how enormous and how generous that aerial world could be. Watch the small shape in the distance, still visible against the clouds, still banking and turning with an ease that looks effortless. It has been flying, in the sense that its lineage has been flying for perhaps a few 100,000 years. It does not know how new it is. It does not know that nothing like it has ever existed before. It knows only the wind beneath its wings, the smell of the sea below, and somewhere in the distance, the silver flash of a fish rising near the surface. It banks toward it and drops, and the sky swallows it whole. The sensory world of a pterosaur is something we can only partially reconstruct. From the size and shape of their preserved brain cases, we know that the portions of the brain associated with vision were enlarged, suggesting that visual acuity was a primary sensory channel. Pterosaur eyes were large relative to skull size, like those of birds of prey, capable of resolving fine detail at considerable distances. The ability to spot a fish moving near the surface of water from a height of 10 or 20 meters, to judge the distance and trajectory of a flying insect against the backdrop of a forest canopy, these were the visual tasks that pterosaur eyes were solving, and the evidence suggests they were solving them well. The brains of early pterosaurs also show enlargement of the regions associated with balance and spatial orientation. The three-dimensional navigation required for powered flight makes demands on spatial processing that walking or swimming does not, and the pterosaur nervous system had responded to this demand with the development of more sophisticated balance organs and the brain circuitry to interpret their signals. Modern birds show similar brain specializations for the same reasons, and the parallel development of enhanced visual and balance processing in two unrelated groups of flying vertebrates is a beautiful example of convergent evolution operating on neural architecture. The reproduction of pterosaurs is a topic that has been illuminated by some remarkable fossil discoveries. Eggs of pterosaurs, preserved in fine-grained sediment, have been found in China and Argentina, and they reveal that pterosaur eggs were relatively soft-shelled, more like the eggs of modern lizards and snakes than the hard-shelled eggs of birds and most modern reptiles. Soft-shelled eggs must be buried in moist soil or sand to prevent desiccation, unlike hard-shelled eggs which can be incubated in the open. This suggests that pterosaurs, like modern soft-shelled egg layers, buried their eggs and left them to develop on their own, with any parental care occurring after hatching rather than during incubation. The young pterosaurs that hatched from these buried eggs faced an immediate challenge. Unlike modern bird chicks, which are helpless at hatching and require extensive parental feeding and protection, pterosaur hatchlings appear to have been relatively well developed, born with fully formed wings and bones dense enough to suggest they were capable of some degree of locomotion from birth. Whether they could fly immediately after hatching or required some period of development before their first flights is debated, but the structural evidence suggests they were more precocial than most modern birds. The diversity of pterosaur feeding strategies was a direct consequence of their ability to access habitats that were unavailable to terrestrial animals. A pterosaur fishing over a lake could exploit resources that were completely inaccessible to any land-based predator. A pterosaur hunting insects over a forest canopy was working in a three-dimensional space that ground-based insectivores could only access partially from below. This ecological independence gave pterosaurs an evolutionary freedom that contributed to the remarkable diversity they achieved over their 160 million-year history. The late Triassic also produced some pterosaurs whose habits and habitats remain mysterious. Eudomorphodon, for all the detail preserved in its Italian fossils, still poses questions about aspects of its biology that the fossil record cannot answer. Where did it roost? How did it court and mate? What were the details of its daily routine, the timing of its flights, the way it spent the hours when it was not actively hunting? These intimate details of ancient animal lives are among the most tantalizing gaps in our knowledge of the past, and they remind us that the fossil record, however rich, gives us only the skeleton of ancient lives, not their flesh. The wing membrane of pterosaurs was reinforced not only by the actinofibrils already mentioned, but also by a complex arrangement of blood vessels whose distribution can be reconstructed from exceptionally preserved specimens. The blood supply to the wing membrane served multiple functions, providing oxygen to the active muscles and tissues of the membrane, and also allowing thermoregulation through the controlled shunting of warm blood to the wing surface for heat dissipation or its retention in the body core for heat conservation. Modern bats use their wing membranes for thermoregulation in a similar way, and the blood vessel patterns in pterosaur wing membranes suggest a similar physiological capability. The study of pterosaur locomotion on the ground has been informed by the discovery of trackways attributed to pterosaurs at several Mesozoic sites. These trackways show that at least some pterosaurs were capable walkers, their four-limbed gait leaving distinctive tracks with hand and foot impressions. The hands of walking pterosaurs struck the ground with the fingers folded back, the wrist joint serving as the primary contact point, a posture that protected the delicate wing membrane from ground contact while still allowing quadrupedal locomotion. This unusual hand posture is inferred from the shape of the hand impressions in pterosaur trackways and has important implications for understanding how pterosaurs spent their time when not flying. They are not impressive. Not yet. You are standing in a dry river valley in what will eventually become Argentina, 230 million years from now, and the creatures moving through the sparse vegetation along the channel banks are not the enormous, world-shaking animals that the word dinosaur conjures. They are small, the largest among them no longer than your arm, and they move quickly and nervously, always watching the space around them, always ready to run. These are Eoraptor or something very like it. Among the earliest known dinosaurs, discovered in the Esquigualasto Formation of northwest Argentina in rocks dated to roughly 231 million years ago. Eoraptor was a small, lightly built bipedal animal, perhaps a meter long and weighing perhaps 5 kilograms, its body balanced over its hind legs in the characteristic dinosaur posture, its small arms held forward, its long tail extended behind it as a counterweight. The name Eoraptor means dawn plunderer, and the name is appropriate though not perhaps in the way it first sounds. These were early animals in the dinosaur story, dawn creatures in a temporal sense, and they plundered opportunities in the way that successful small opportunists always do, quickly, constantly, without commitment to any single strategy. Their teeth were mixed, some serrated and sharp for processing meat, others more leaf-shaped and suitable for plant material, suggesting a genuinely omnivorous diet that would take whatever presented itself. The world around Eoraptor was not yet a dinosaur world. The dominant animals were still the Rauisuchians, large predatory archosaurs with massive heads and powerful jaws, some of them exceeding 5 meters in length. The Atosaur, those armored herbivores the size of small cars, were common. The Rhynchosaurs, beaked herbivores that have been found at numerous Triassic sites across the globe, were particularly abundant in some regions, their fossils often comprising the majority of the large vertebrate fauna at sites where they occurred. And yet the dinosaurs were there. Present if not dominant. Moving through the world that the Rauisuchians and Aetosaur and Rhynchosaurs controlled, eating the food that was left after the larger animals had eaten, occupying the marginal habitats that the dominant species had not gotten around to claiming. In the language of ecology, they were subordinate species, filling the gaps in a community structured by larger, more established animals. What made dinosaurs different from the other archosaurs? What advantage did they have that would, in the long run, allow them to outlast and outcompete the groups that dominated them in their early years? The answer is not a single thing. It is a constellation of small advantages that individually might not have been decisive but together created an animal that was unusually well positioned for the changes that were coming. The most discussed of these advantages is posture. Dinosaurs walked with an upright, fully erect posture, their legs positioned directly beneath their bodies rather than at an angle to either side. This posture, which they share with birds and mammals and which is different from the sprawling posture of most modern reptiles, has significant biomechanical advantages. An upright animal can breathe freely while running because its trunk does not flex laterally with each stride, unlike a sprawling animal whose ribcage is compressed and expanded by the same muscles that move its limbs. This means that dinosaurs could sustain aerobic activity for much longer than sprawling animals of similar size. The respiratory system of dinosaurs may have been another crucial advantage. Modern birds, which are living dinosaurs, have an extraordinarily efficient respiratory system built around a series of air sacs that keep air flowing continuously through the lungs in one direction, extracting far more oxygen per breath than the tidal breathing of mammals or the even less efficient systems of most reptiles. The bone structure of many dinosaurs, particularly the hollow vertebrae and ribs, suggests that this avian-style respiratory system was already present, or at least partially developed, in the earliest dinosaurs. Metabolic rate is another factor. The evidence for dinosaur metabolism is complex and contested, but the balance of current research suggests that most dinosaurs were not fully ectothermic in the way that modern lizards and crocodiles are. They may have occupied a position somewhere between modern reptiles and modern birds and mammals, running warmer and faster than a crocodile but perhaps not quite as consistently active as a warm-blooded mammal. Whatever the exact metabolic status of early dinosaurs, the evidence from their bone growth patterns suggests they grew faster than most modern reptiles, which in itself suggests a more active metabolism. There is also the question of behavior. Dinosaurs as a group were probably more behaviorally sophisticated than many of their contemporaries. Evidence from nest sites, from social groupings, from the complexity of their sense organs, suggests animals with greater capacity for flexible responses to environmental challenges than many of the other Triassic vertebrates. Behavioral flexibility is an enormously valuable trait in a changing world, and the Triassic, as we know, was about to change dramatically. The Herrerasaurus, another early dinosaur from the Esquigualasto Formation, was larger than Eoraptor and clearly more predatory. Herrerasaurus reached lengths of 3 to 6 meters and was equipped with a mouthful of recurved, serrated teeth that are unmistakably the teeth of an active carnivore. Its hand had 3 large, grasping fingers with sharp claws. Its hind limbs were long and powerful, built for speed. It was not the biggest predator in its ecosystem, the large Rawasuchians held that title, but it was an effective hunter that was clearly carving out a niche for itself in the late Triassic carnivore community. The earliest herbivorous dinosaurs were also appearing in the late Triassic. Some early sauropodomorphs, the lineage that would eventually produce the enormous long-necked giants of the Jurassic and Cretaceous, were present and beginning to explore the herbivore niche that would eventually become so important. Early sauropodomorphs like Panphagia and Pampodromius were small, perhaps a meter or 2 long, and probably facultatively herbivorous, capable of eating both plant material and small animals. The Ornithischian dinosaurs, the lineage that would eventually produce the horned ceratopsians, the armored ankylosaurs, the plated stegosaurs and the duck-billed hadrosaurs, were also beginning their evolutionary story in the late Triassic, though their early representatives were small and not yet recognizable as the ancestors of those later giants. Pisanosaurus, from Argentina, is one of the oldest potential ornithischians, a small herbivore from the same formation as Eoraptor and Herrerasaurus. The dinosaur family tree was branching. Quietly, at the margins of ecosystems dominated by other animals, the fundamental divisions of what would become the dinosaur empire were being laid down. Sauropodomorphs and theropods were diverging from each other and from the ornithischians. Body plans were being tested and selected. Anatomical features that would eventually define whole lineages were appearing in their primitive forms. The future was being written in the bones of small animals moving cautiously through a world that did not yet belong to them. It is important not to read purpose into this. The early dinosaurs were not becoming dominant because they were trying to. They were not aware of the ecological revolution they were part of. They were simply doing what animals do, finding food, avoiding predators, reproducing. The patterns that would eventually lead to their dominance were emerging from the blind mechanics of natural selection, from the accumulated effect of tiny differences in survival and reproduction across thousands of generations. What is remarkable, looking back, is how brief the period of dinosaur subordination actually was. From the first known dinosaurs, roughly 231 million years ago, to the beginning of clear dinosaur dominance, roughly 215 to 210 million years ago, was perhaps 20 million years. In geological terms this is not long. In evolutionary terms it is not long. The transition from marginal to dominant happened with a speed that surprises even paleontologists who study it. The sun is setting over the Esquigualasto Valley. The light is that particular amber of subtropical dusk, warm and long, and the small dinosaurs are becoming more active as the temperature drops from its midday peak to something more comfortable. They are moving along the river bank, turning over stones with their small hands, investigating the base of vegetation clumps, doing the patient work of small omnivores everywhere and in every time. They do not know what they are. They do not know what they will become. They are simply alive, and the world around them is simply the world, ordinary in its way, unremarkable in its way. Though of course it is neither. The feet of early dinosaurs tell their own story. The 3-toed foot, with the middle toe the longest and the first and third toes flanking it, is a distinctive structure that appears in the earliest dinosaurs and persists with variations through the entire subsequent history of the group. The trackways that dinosaurs left in soft sediment have been found at dozens of Triassic sites, and they reveal information about gait, speed, and behavior that skeletal fossils alone cannot provide. A bipedal dinosaur moving across a mudflat, its tracks preserved in the sediment and eventually lithified into rock, is communicating across 230 million years about the mechanics of its movement. The question of dinosaur intelligence is one that is difficult to address from fossil evidence but important for understanding their eventual success. Brain size relative to body size, a rough proxy for cognitive capacity, can be estimated from endocasts, the natural or artificial molds of the interior of the brain case. Early dinosaur endocasts show brain sizes that are broadly similar to or slightly larger than those of other archosaurs of similar body size, not dramatically larger, not suggesting the kind of cognitive leap that would make them obviously superior in intelligence to their contemporaries. What the early dinosaurs may have had that many of their contemporaries lacked was behavioral flexibility, the capacity to adjust their responses to novel situations rather than relying exclusively on fixed behavioral responses. Modern birds, which are living dinosaurs, show remarkable behavioral flexibility, including problem-solving, tool use, and complex social learning. If the dinosaur lineage had elevated behavioral flexibility from its earliest stages, this would have been a significant advantage in the changing conditions of the late Triassic, allowing early dinosaurs to exploit new resources and adapt to new habitats faster than competitors with more rigid behavioral repertoires. The color of early dinosaurs is another question that fossil bones cannot directly answer but that modern techniques are beginning to illuminate. Fossil feathers from much later dinosaurs have been analyzed using scanning electron microscopy and have revealed the presence of melanosomes, the organelles that produce the pigments responsible for color in modern feathers. The shapes of these melanosomes correlate with the colors they produce in modern birds, allowing researchers to reconstruct the colors of at least some dinosaurs. For the earliest dinosaurs of the Triassic, which were not feathered in any preserved sense, we are left to speculate based on what we know of color function in living reptiles. The territorial behavior of early dinosaurs, if they were territorial, would have influenced their distribution across the landscape and the genetic structure of their populations. Modern reptiles show a wide range of territorial behaviors, from species that defend large exclusive territories to species that are entirely non-territorial and coexist in dense aggregations. The ecological context of the early dinosaurs, small predators in an ecosystem still dominated by larger archosaurs, might have favored a flexible approach to territoriality, defending resources when competition was intense but coexisting when resources were abundant. The bones of dinosaurs record their growth histories in a way that is unique among reptiles. The presence of bone growth rings, annual lines of arrested growth similar to the growth rings in trees, allow researchers to determine the age of individual specimens at death and to calculate growth rates. Early dinosaur growth rates appear to have been faster than those of typical modern reptiles but slower than those of birds and mammals. This intermediate growth rate is consistent with an intermediate metabolic rate, and it tells us that the dinosaurs were, from their very beginnings, doing something different from the typical reptilian growth pattern. The skin texture of early dinosaurs is preserved at a handful of fossil sites where exceptional conditions mummified or dried the remains before they could decay. These impressions show a covering of small, non-overlapping scales, different from the large, overlapping scales of many modern reptiles but similar to the small scales that cover the feet of modern birds. The scale pattern varied across the body, with different regions showing different scale sizes and arrangements, and the overall texture was probably less conspicuous than the bold scale patterns of many modern lizards. Some early theropod dinosaurs from slightly later in the Jurassic show evidence of feather-like structures on parts of the body, and the question of whether the earliest dinosaurs had any proto-feathery structures on parts of their bodies is one that current research has not fully resolved. The egg-laying behavior of early dinosaurs is one of the most intimate aspects of their biology that the fossil record occasionally illuminates. Nests of early dinosaurs are known from several Triassic and early Jurassic sites, and they show a range of nesting strategies. Some early dinosaurs apparently buried their eggs in mounds of vegetation, like modern megapode birds, relying on the heat of decomposition to incubate them. Others laid eggs in simple scrapes in the ground, perhaps covering them with sand or soil. The variety of nesting strategies visible even in the earliest dinosaurs is a measure of the behavioral flexibility that would characterize the group through its entire subsequent history. The question of how and why the dinosaurs rose to dominance in the late Triassic, while their competitors declined, has occupied paleontologists for decades. The older view, sometimes called the competitive displacement hypothesis, held that dinosaurs actively outcompete their rivals through superior traits, that their upright stance and elevated metabolism and efficient respiratory systems made them better at finding and processing food, better at escaping predators, better at reproducing, and that this superiority drove the Rauisuchians and Rhynchosaurs and other groups to extinction by direct competitive exclusion. More recent research has complicated this picture considerably. The evidence from the fossil record now suggests that the rise of dinosaurs was less a story of competitive triumph than of opportunistic diversification following extinction events. The end Carnian faunal turnover, associated with the Carnian pluvial episode, eliminated many of the groups that had dominated the Middle Triassic. The end Triassic extinction eliminated many more. Dinosaurs did not cause these extinctions. They survived them, and in the ecological space opened by the dying of their competitors, they diversified. This pattern, of marginal groups inheriting the world after catastrophe rather than conquering it in direct competition, appears repeatedly in the history of life. The earliest dinosaurs were small enough to be overlooked in a fauna dominated by much larger animals. Allosaurus, from the late Triassic of Argentina, was a significant predator by dinosaur standards but would have seemed modest compared to the Rauisuchians that occupied the apex predator role in many late Triassic ecosystems. Eoraptor, another early Argentinian dinosaur, was even smaller, a lightly built biped that probably fed on small prey and invertebrates. These were not the animals that commanded the landscape. They were the animals living in its margins, exploiting the resources that the larger, dominant animals ignored or could not access. The geographic distribution of the earliest known dinosaurs is concentrated in what was then the southern portion of Pangaea, the region that would become South America and parts of Africa. This concentration may reflect the actual pattern of dinosaur origins, with the lineage first appearing in the tropics and subtropics of the southern supercontinent and then spreading northward and across the rest of Pangaea as conditions changed and barriers were reduced. Or it may reflect the accidents of fossil preservation and discovery, with Triassic rocks suitable for preserving dinosaur fossils being more abundant and more thoroughly explored in Argentina and Brazil than in some other regions. Distinguishing between these two possibilities is one of the ongoing challenges of Triassic paleontology. If you are feeling the weight of sleep now, let it come. The ancient world will be here when you return to it. Subscribe so the next story finds you easily. And if you are still with us, still moving through this ancient landscape, then walk on. There is more ahead. There is a particular quality of stillness that belongs to animals that have been shaped by hundreds of millions of years of selection for patience. You find it in herons, standing motionless at the water's edge for hours waiting for a fish to come within reach. You find it in crocodiles, floating with their eyes just above the surface, so still that they might be a floating log if not for the faint pulse of breathing visible at their flanks. And you find it, here on the shore of a late Triassic river, in a creature that is pulling its limbs slowly toward its body and settling into a posture of absolute rest on a flat rock in the afternoon sun. The turtle is watching you. Or perhaps it is not watching you exactly. Perhaps watch implies too much intentionality for an animal whose eyes are open but whose attention is diffused across its entire warm surroundings without particular focus. It is aware of you in the way that a very old, very settled creature is aware of things, noting your presence, assessing the degree of threat you represent, and concluding, in whatever way turtles conclude things, that you do not merit movement. The turtle is Progonocales, one of the earliest known members of the turtle lineage from the late Triassic of Europe. It is about 60 centimeters long, smaller than many modern tortoises, with a fully developed shell that covers both its back and its belly. The shell is not an add-on, not a structure built around an existing animal. It is integral to the animal skeleton, the ribs broadened and fused into the upper shell, the belly bones reorganized into the lower shell, in a transformation of vertebrate anatomy so thorough and so complete that paleontologists spent many years wondering how it could have happened. The evolution of the turtle shell is one of the most fascinating anatomical puzzles in paleontology. It represents such a radical reorganization of vertebrate trunk anatomy that for a long time researchers could not identify convincing transitional forms between ordinary reptiles and turtles. The ribs had to move outside the shoulder girdle, which is anatomically extraordinary. No other vertebrate has ribs in that position, and the process by which this happened required a sequence of developmental changes, each of which had to be adaptive in its own right. Recent discoveries have helped clarify the picture. Fossils from the Middle Triassic of China and Germany show animals with partially developed turtle-like features, broad ribs beginning the process of expansion that would eventually produce the shell, even though the upper and lower shells were not yet connected. These animals, like Popocheles and Odontocheles, show that the turtle body plan evolved gradually, step by step, over millions of years, each incremental change providing some functional advantage, perhaps stability for burrowing, perhaps protection from particular predators, even before the full shell was in place. Progonocales already had the full shell, but it differed from modern turtles in important ways. It could not retract its head into its shell, the neck was too short and the shell geometry did not allow for the folding mechanism that modern turtles use. Instead, it had defensive spines on its neck and head, providing some protection for the parts that the shell could not cover. Its teeth were not quite absent, though they were vestigial, small and non-functional, on the way to the completely toothless condition of all modern turtles. The crocodilians were taking their shape in the late Triassic as well, though the early members of their lineage were strikingly different from the animals we know today. The earliest crocodilomorphs, the group that includes modern crocodilians and all their extinct relatives, were predominantly terrestrial animals. They did not lurk in rivers waiting to ambush prey at the water's edge. They ran across the open ground on legs that were, in some lineages, remarkably upright and slender, more like the legs of a fast-running dog than the sprawling limbs of a modern crocodile. Pterostricus, from the late Triassic of Wales, was perhaps the most extreme example. This animal was slender and agile, roughly a meter long, its legs long and positioned nearly beneath its body, its snout narrow and equipped with small, sharp teeth suitable for catching insects and small vertebrates. It would not have looked much like a crocodile to a modern observer. It would have looked, in fact, rather like a small and fast-running archosaur of no particular family, which is precisely what it was in the process of becoming. The transition from terrestrial to semi-aquatic lifestyles happened independently in several crocodilomorph lineages through the late Triassic and into the Jurassic. The water offered enormous opportunity, particularly in the expanding river and lake systems of the late Triassic world. Fish were abundant in these waterways, many of them species that had never evolved alongside the particular hunting strategies of a large aquatic ambush predator, which meant they had no defensive behaviors adapted to avoid one. The Sphenosuchians were another important group of Triassic crocodilomorphs, occupying a range of ecological roles across both terrestrial and semi-aquatic habitats. Some were small, lightly built forms that may have been primarily insectivorous. Others were more robust, with teeth that suggest they were taking larger prey. The diversity of the group even at this early stage was a sign of evolutionary potential, of a body plan flexible enough to be adapted to a wide range of conditions. The phytosaurs, though not closely related to crocodilians, deserve mention here because they occupied the semi-aquatic ambush predator niche that crocodilians would eventually take over. Phytosaurs are one of the most striking examples of convergent evolution in the fossil record. These archosaurs had long, narrow snouts packed with conical teeth, heavily armored bodies, and short, powerful limbs, an anatomy so similar to modern crocodilians that when they were first discovered in the 19th century, researchers assumed they were ancestral to crocodiles. The key anatomical difference between phytosaurs and true crocodilians is the position of the nostrils. In phytosaurs, the nostrils are positioned not at the tip of the snout but far back on the top of the skull, close to the eyes, so that the animal could breathe while the long snout was submerged. In modern crocodilians, the nostrils are at the tip of the snout. This difference in nostril position, seemingly minor, is actually a fundamental distinction that reflects the completely different evolutionary histories of the two groups. Phytosaurs were widespread and diverse in the late Triassic, found at sites across North America, Europe, Africa, and Asia. Some were large animals, reaching lengths of 5 or 6 meters, the dominant predators of the large river and lake systems that were expanding through the Triassic landscape. They would disappear entirely at the end of the Triassic, leaving the semi-aquatic predator niche temporarily empty, only for the crocodilomorphs to fill it in the Jurassic with the body plan that has persisted largely unchanged for 200 million years since. The lizard-like lepidosaurs, another important group of Triassic reptiles, were also diversifying steadily. The lepidosaurs are the group that today includes lizards, snakes, and the tuatara, that living fossil from New Zealand that is the sole survivor of an ancient lineage. In the Triassic, lepidosaurs were small, generally insectivorous animals that occupied the understory of forests and the margins of other habitats. They were not dominant. They were persistent. The rhynchosaurs, those beaked herbivores that were so abundant in many Triassic assemblages, were themselves a lepidosaur lineage, though a very specialized one. Their strong beaks and crushing back teeth were adapted for processing hard seeds and roots, and their abundance at many sites suggests they were filling the ecological role that medium-sized herbivores play in modern ecosystems. They would not survive the end of the Triassic, but while they lived they were important components of the terrestrial ecosystem. All these creatures, the turtles and crocodilomorphs and phytosaurs and rhynchosaurs, were part of a Triassic ecosystem that was becoming increasingly complex and diverse. The empty spaces that the Great Dying had created were filling steadily. The food webs were developing more links, more redundancy, more of the interlocking dependency that makes a stable ecosystem resilient to perturbation. The world was becoming what it needed to be. The turtle on the rock has closed its eyes. Whether it is asleep or simply in that state of deep physiological repose that turtles can achieve while remaining technically awake is unclear. Its breathing is barely visible, a slow expansion and contraction of the edges of its shell where the neck and leg openings allow slight flexion. The river moves past it with the unhurried persistence of water that has been moving in one direction for millions of years and expects to keep doing so. This scene, this particular combination of warm rock and moving water and an ancient creature at rest in the afternoon sun, will persist in essence through the rest of geological time. The specific animals will change. The The specific trees overhanging the bank will change. The specific chemistry of the water will shift subtly over millions of years. But the broad shape of it, the river, the rock, the basking animal, this will endure because it is a relationship between organism and environment that works, that has been proven to work, that will go on being proven to work long after everything else about this world has been transformed beyond recognition. The armor of the Allosaurus was not merely protective. It was also a form of identity, a species-specific pattern of plate shapes and sizes that could be recognized by other members of the species. Modern armadillos, which have a similarly extensive armor covering, show individual and subspecific variation in their armor patterns, and there is no reason to think that Allosaurus were different. The ability to recognize conspecifics through visual cues is important for social behavior, including mating and the maintenance of social hierarchies, and the complex patterns of Allosaur armor may have been as much a social signal as a physical defense. The jaw anatomy of phytosaurs reveals details about their feeding behavior that go beyond the simple observation that they were piscivores. The long, narrow snout concentrated the force of the jaw closure into a small area, maximizing the speed of the strike at the cost of bite force. This is exactly the right trade-off for an animal catching fast-moving fish, where the speed of the snap is more important than the crushing power of the bite. Phytosaur teeth were not merely sharp, they were oriented to prevent captured fish from wriggling free, their interlocking structure creating a cage around any fish that was caught. The crocodilomorphs of the Triassic were experimenting with a range of ecological roles that would eventually narrow considerably as their descendants converged on the semi-aquatic ambush predator body plan. Some Triassic crocodilomorphs were herbivores, their teeth flattened and broadened for processing plant material. Others were specialized insectivores with delicate skulls and numerous small teeth. The diversity of this early experimentation is a reminder that the modern crocodilian body plan is not the only possible solution to the challenges of archosaur existence, but one of many solutions that was tested and found to have particular long-term viability. The taphonomy of late Triassic fossil sites, the study of how organisms died and were preserved, tells stories that go beyond the mere existence of the organisms themselves. Sites where multiple individuals of the same species are found together can indicate social aggregations, or they can indicate natural traps that caught multiple animals over time, or they can indicate catastrophic death events that killed many animals simultaneously. Distinguishing between these possibilities requires careful analysis of the relationships between individual specimens, the chemistry of the sediment, and the evidence of any other organisms present at the site. The late Triassic was also the time when the first lizards in the modern sense were beginning to appear. The lepidosaurs had been present since the Permian, but through the early and middle Triassic they had been relatively conservative in their evolution, not yet producing the extraordinary diversity of forms that characterizes modern lizard fauna. The late Triassic saw the first clearly recognizable lizard-grade lepidosaurs, animals with the distinctive skull structure and jaw mechanics that define the lizard lineage. These early lizards were small insectivores, occupying the smallest body size classes of the Triassic vertebrate community. The persistence of large archosaur groups like the Rawasuchians and Allosaur alongside the early dinosaurs through much of the late Triassic is a reminder that the transition to dinosaur dominance was not sudden or inevitable. For many millions of years, the dinosaurs were genuinely subordinate to these other groups, and the eventual decline of the non-dinosaurian archosaurs appears to have been driven primarily by the end-Triassic extinction rather than by competitive displacement by the dinosaurs. The extinction gave the dinosaurs their opportunity. Without it, the outcome might have been very different. The biomechanics of the Rawasuchian archosaurs, those large predatory animals that dominated the terrestrial carnivore guild for much of the Triassic, have been reconstructed from their skeletal remains with considerable detail. Their locomotion was more variable than that of dinosaurs, some species having a more upright posture and others a more sprawling one, and this variability may have contributed to their eventual replacement by the more uniformly upright and energetically efficient dinosaurs. The largest Rawasuchians, with skulls over a meter long and bodies approaching the size of modern large crocodilians, were formidable animals, but their locomotor efficiency appears to have been lower than that of the increasingly diverse dinosaur fauna developing alongside them. The trace fossil record of late Triassic terrestrial environments preserves aspects of animal behavior that body fossils cannot. Burrows attributed to various tetrapods show the variety of below-ground habitats that animals were exploiting. Feeding traces on fossil wood and plant material document the activities of wood-boring insects and wood-eating vertebrates. Coprolites, fossil excrement, preserve information about diet that is not always recoverable from teeth and jaw morphology alone. Some late Triassic coprolites contain identifiable remains of specific food items, including fish scales, insect exoskeletons, and plant fragments, and these chemical and structural remnants of meals eaten 220 million years ago are among the most intimate records the fossil record provides of the daily lives of Triassic animals. Come down. Come away from the open spaces and the large animals. Come into the close, damp spaces near the base of an ancient conifer, where the roots make a network of partial shelters in the soil and the leaf litter is thick and smells of fungus and decay and the small chemistry of decomposition. Here, in these intimate spaces, in the darkness between roots and under bark and in the narrow tunnels that have been pressed through the soil by years of repeated use, something is moving that will matter more to the long-term future of life on Earth than any of the large and impressive animals we have been watching. The cynodont is small. Perhaps 20 centimeters from nose to the base of its tail, the tail itself adding another 10. It weighs perhaps as much as a small sandwich. It is moving through the leaf litter with a quick, purposeful efficiency, its nose pressed close to the ground, its whiskers, and yes, it has whiskers, tracing the contours of the surface around it as it searches for the particular scents that indicate food. Its head is disproportionately large for an animal of its size, housing a brain that is, relative to its body, more developed than those of the other reptiles around it. The temporal region of the skull, behind the eye socket, is expanded to accommodate larger jaw muscles, a sign of more powerful and precise biting than is possible for animals with simpler skulls. Its teeth are differentiated, incisors at the front for cutting and gripping, canines behind them for puncturing, and cheek teeth, molars and premolars, that occlude precisely when the jaws close, the upper and lower teeth fitting together in a way that allows them to cut food rather than simply crushing it. Differentiated teeth are enormously significant. Modern mammals have them too, and this is not a coincidence. The cynodont is on the evolutionary path that leads, eventually, to every mammal that has ever lived, and the differentiation of its teeth is one of the most important early milestones on that path. A mammal's teeth are one of the primary reasons for its ecological success. Incisors, canines, and molars together allow an animal to exploit a much wider range of food types than an animal with uniform teeth can manage, and this dietary flexibility is a key component of the mammalian success story. The cynodont pauses over something in the leaf litter. A large beetle, nearly a centimeter long, has been exposed as the cynodont's explorations turned over a piece of bark. For a fraction of a second the beetle and the cynodont are both still. Then the cynodont's head darts forward and the beetle is gone. The cynodont chews briefly, the specialized cheek teeth doing their work, and moves on. This interaction, tiny and quiet and taking less than a second, is a preview of 10,000 similar interactions across the history of mammal evolution, the quick, efficient harvest of energy from the world's invertebrate bounty. The cynodonts had survived the Permian-Triassic extinction against the odds. Like most surviving synapsid lineages, they had been reduced to a handful of species in a few refugia, and the early Triassic had been a difficult period of recovery. But they were robust animals, and the traits that defined them were particularly well suited to the recovery environment. Their flexible diet allowed them to exploit whatever food sources were available. Their more active metabolism allowed them to remain active in a wider range of conditions than cold-blooded contemporaries. Their burrowing ability protected them from the temperature extremes of the post-extinction world. Through the Middle and Late Triassic, the cynodonts diversified considerably. The herbivorous cynodonts, the traversidonts, developed complex cheek teeth with a sophisticated shearing surface that could process plant material with considerable efficiency. They grew to moderate sizes, some reaching the size of a large dog, and their abundance at certain fossil sites suggests they were important components of the herbivore community in some regions. The carnivorous cynodonts diversified as well, some retaining the small insectivore body plan, others growing larger and moving toward more vertebrate prey. The chiniquodonts, for example, were moderate-sized predators with well-developed canine teeth and a skull shape that suggests a powerful, direct bite. They were not the apex predators of their ecosystems, that role was held by the larger archosaurs, but they were effective secondary predators filling niches between the giants. What is most fascinating about the cynodonts, beyond their own ecological success, is the window they provide into the evolution of mammalian traits. Every feature that defines modern mammals, warm blood, hair, differentiated teeth, a specific jaw joint, the particular bones of the middle ear, live birth, parental care, these features did not appear all at once in a single ancestral species. They accumulated incrementally, one or two at a time, across tens of millions of years of cynodont evolution, with each feature providing some advantage to the animals that possessed it. The jaw joint is perhaps the most remarkable of these transitional features. Modern mammals have a jaw joint formed by two specific bones, the squamosal and the dentary. Modern reptiles have a jaw joint formed by a different set of bones, the quadrate and the articular. The evolutionary transition between these two configurations required the quadrate and articular bones to migrate out of the jaw joint and into the middle ear, where they became the tiny bones, the incus and malleus, that conduct sound to the cochlea in all living mammals. This seems impossibly strange that the bones of the jaw could become the bones of the ear, and yet the evidence for this transformation is written clearly in the bones of transitional cynodonts. In the most advanced cynodonts, the jaw joint involves both the old reptilian bones and the beginnings of the new mammalian configuration, both present simultaneously, a biological compromise that foreshadows the solution without quite committing to it. The transitional fossils are extraordinary precisely because they capture this moment of in-betweenness. The question of warm blood in cynodonts is difficult to resolve definitively from fossil evidence, but the balance of evidence suggests that at least some cynodont lineages had elevated metabolic rates compared to typical reptiles. Bone growth patterns in some species suggest rapid growth more consistent with endothermy than ectothermy. The development of whiskers, which are sensory organs associated with neural infrastructure that is metabolically expensive and more consistent with a warm-blooded physiology, suggests elevated activity levels. The dental complexity, which requires more active and searching behavior to make full use of, points in the same direction. Parental care is another area where the cynodonts may have been pioneers. Direct evidence for parental behavior in extinct animals is rare, but there are Triassic fossil sites where cynodont specimens of multiple ages are found together in what appears to be a social grouping, potentially a family unit. The development of increasingly complex social behaviors, including parental care, is strongly correlated in living mammals with endothermy, because the metabolic capacity for sustained activity makes it possible to invest significant time and energy in offspring. The story of the cynodonts is in some ways the most intimate story of the Triassic, the story of small, warm-blooded, caring, complex-brained animals finding their way in a world that was mostly managed by larger, colder, simpler creatures. They were not impressive by the standards of their time. They left smaller footprints than the Rawasuchians, smaller bones than the early sauropodomorphs, smaller presence in the fossil record than the phytosaurs. But they were carrying, in their differentiated teeth and their expanding brains and their elevated metabolisms, a set of evolutionary investments that would eventually pay the greatest dividend in the history of vertebrate life on Earth. When the dinosaurs eventually took over the terrestrial ecosystem in the late Triassic and Jurassic, they did not eliminate the cynodonts and their descendants. They compressed them. The true mammals, the direct descendants of advanced cynodonts, survived the dinosaur age not by competing with dinosaurs directly but by occupying niches that dinosaurs could not exploit effectively: small body sizes, nocturnal activity, flexible diets, burrowing lifestyles. For 165 million years, the mammals lived in the margins, small and mostly nocturnal, while the dinosaurs ruled the light. But margins can be productive places. The selection pressures of small size and nocturnal life drove further refinements in brain development, sensory capability, social complexity. By the time the dinosaurs went extinct 66 million years ago, the mammals that had been waiting in the shadows had become extraordinarily capable animals, ready to expand into the ecological space that the dinosaur extinction created. Everything that came after, every whale and elephant and bat and human being, traces its ancestry back through the long tunnel of mammalian evolution to the advanced cynodonts of the Triassic, to animals like the one now disappearing back under the conifer roots, carrying its beetle, returning to the darkness and warmth of its burrow, its small heart beating fast and steady in the Triassic night. The hearing capabilities of advanced cynodonts were in the process of transformation during the Triassic, as the jaw bones that had been part of the hearing apparatus in simpler animals were migrating toward the ear region. This migration produced, as an intermediate stage, animals whose hearing was conducted through both the old jawbone pathway and the new dentary-based pathway simultaneously. The dual hearing system would have been unusual by modern standards, but it worked, and the gradual improvement of the new pathway gave the lineage that led to mammals increasingly acute hearing that would eventually make them among the best hearing animals on Earth. The sense of smell in cynodonts was also undergoing significant development. The olfactory region of cynodont skulls is enlarged relative to earlier synapsids, and the turbinate bones inside the nasal passages, which in modern mammals serve to warm and humidify inhaled air as well as to vastly expand the surface area available for olfactory receptor cells, appear to have been developing toward the mammalian condition. Enhanced olfaction is particularly valuable for nocturnal animals, which cannot rely on vision in low-light conditions, and the development of better smell in the cynodont lineage may be one of the earliest signs of the nocturnal lifestyle that would characterize the early mammals. The diet of advanced cynodonts was increasingly omnivorous, with different species occupying different positions on the spectrum from primarily insectivorous to primarily herbivorous. The herbivorous cynodonts, the traversodonts, developed particularly complex cheek teeth with multiple cusps that could shear and grind plant material with considerable efficiency. These teeth represent a significant advance over the simpler crushing teeth of earlier herbivores, and the efficiency of food processing they allowed may have contributed to the success of these animals in the Middle and Late Triassic. The burrowing behavior of some cynodont species is documented by the finding of fossils in what appear to be natural burrow casts, situations where animals died in their burrows and the burrows were subsequently filled with sediment that preserved the shape of the structure. These burrows are not elaborate structures by modern mammal standards, but they represent a significant behavioral development, the creation of a controlled microenvironment that moderates temperature extremes and provides protection from predators. The ability to thermoregulate behaviorally through burrowing was important for animals that were in the process of transitioning toward endothermy. The cynodont fossil record includes some remarkable preservation of soft tissues that gives us glimpses of aspects of cynodont biology that bones alone cannot reveal. Impressions of skin in a few specimens suggest a covering that was neither fully scaly like a typical reptile nor fully furred like a modern mammal, but something intermediate, perhaps sparse fur or vibrissae, tactile whiskers, over a surface that retained some scale-like structures. This intermediate condition is exactly what we might expect from an animal transitioning between reptilian and mammalian skin types. As the Triassic moved toward its end, the cynodonts and their descendants were becoming more mammal-like in the specific technical sense that the jaw joint was approaching the mammalian configuration, with the dentary bone becoming dominant and the old quadrate and articular bones progressively reduced. Some of the most derived late Triassic cynodonts, the animals sometimes called the first true mammals, had completed this transition, their jaw joint fully mammalian in its mechanics. These animals, small and nocturnal and insectivorous, were the direct ancestors of every mammal alive today. The evolutionary history of hair is one of the most debated topics in the study of synapsid evolution. Modern mammals are defined partly by their hair, and the question of when hair first appeared in the mammal lineage is important both for understanding mammalian biology and for understanding the physiology of the transitional cynodont forms. The fossil record does not preserve soft structures like hair well, but there are indirect lines of evidence. Some Triassic cynodont skulls show pit patterns on the snout that are interpreted as having housed whisker-bearing follicles, similar to the follicles in modern mammals. If these pits did house large tactile whiskers, it implies a level of neural sophistication and possibly a level of insulative fur elsewhere on the body that is consistent with a partially endothermic physiology. The milk glands of modern mammals, which define the class Mammalia as much as any other feature, have no direct fossil record. But the inferred dietary needs of young cynodonts and early mammals, combined with the evidence for extended parental care in some lineages, suggest that some form of nutritive secretion for young may have developed early in the cynodont lineage. Whether this was true lactation in the mammalian sense or a more primitive secretion from skin glands is impossible to determine from the fossil evidence alone. What is clear is that by the time the first true mammals appeared in the late Triassic, the evolutionary trajectory toward mammalian reproductive strategies was well established. The relationship between early cynodonts and the sensory world they inhabited was different in important ways from the sensory world of the archosaurs that dominated the Triassic landscape. The cynodont skull preserves evidence of whiskers in the form of small pits on the snout bones where whisker nerves passed through, suggesting tactile sensitivity that would have been valuable in the dark environments where many cynodonts were active. The evolution of an outer ear capable of detecting airborne sound, rather than relying primarily on vibrations transmitted through the skull bones, was another development occurring in the cynodont lineage through the Triassic, and the modification of jaw bones that would eventually become the mammalian middle ear bones was underway in advanced cynodonts. The brain size of advanced cynodonts, relative to body size, was larger than that of most contemporary reptiles, though still far smaller than that of modern mammals. This relative increase in brain size reflects the more complex behavioral repertoire that cynodonts were developing, the more sophisticated processing of sensory information required for the active, nocturnal lifestyle that many of them pursued, and perhaps the cognitive demands of the social behaviors and parental care strategies that cynodont evidence suggests were present. The evolutionary trajectory toward the very large mammalian brain of the present was beginning in the Triassic, driven by the particular ecological niche that the cynodonts occupied. The fossil sites that preserve cynodont remains sometimes offer glimpses of their lives at a resolution that larger animals rarely achieve. Small burrow structures associated with cynodont fossils from several Triassic localities suggest that these animals were excavating shelters, places of refuge from the heat of the Triassic day and the predators that were active during daylight hours. Burrowing is a behavior that requires a degree of physical effort and planning, and the presence of burrows associated with cynodont remains as evidence of a behavioral complexity that sets these animals apart from the more passive shelter-seeking of typical reptiles. The burrow as a constructed home rather than a found shelter is a step toward the complex home-building behaviors of later mammals. Something is changing. You can feel it in the air, a new quality of moisture that was not present in the last season or the season before that. The sky, which has been the pale, cloudless dome of the dry Triassic interior for as long as you have been standing here, is developing a different character. There are clouds now, low and dense along the horizon in the mornings, building through the afternoons into towers of white and gray that reach high into the atmosphere before spreading out at their tops in the distinctive anvil shapes of mature thunderstorm systems. And then it rains. The Carnian pluvial episode is one of the most dramatic climate events in the Triassic record, a shift from the relatively arid conditions of the Middle Triassic to a substantially wetter climate that persisted for roughly 2 million years, beginning approximately 234 million years ago. The trigger, as so often in Earth's history, was volcanic. A large igneous province, the Rangelia terrane, was erupting with the sustained intensity of a flood basalt event, pumping enormous quantities of carbon dioxide and other greenhouse gases into the atmosphere over hundreds of thousands of years. The greenhouse warming that followed increased global temperatures and, crucially, increased the energy available to drive the hydrological cycle. Warmer air holds more moisture. Warmer oceans evaporate more freely. The monsoon systems that already dominated Triassic climate intensified dramatically, driving moisture further into the continental interior than it had reached in millions of years. Areas that had been stable semi-deserts for the entire early and middle Triassic found themselves receiving rainfall measured not in centimeters but in meters per year. The effects on the landscape were immediate and transformative. The red sandstones and evaporite deposits that characterize the dry Triassic record give way, in the geological sequence from the Carnian stage, to gray-green sediments deposited by rivers and lakes, to coal-bearing sequences indicating the accumulation of organic matter in permanently waterlogged swamps, to the limestone deposits of freshwater lakes that persisted for thousands of years. The rocks changed color, and in that color change is written the story of a world being remade by water. The forests expanded. The seed ferns and conifers and cycads that had occupied the coastal fringes and river valleys spread inland, following the advancing frontier of reliable rainfall, colonizing terrain that had been bare rock and shifting sand for tens of millions of years. The pace of this expansion was rapid in geological terms. Within perhaps a few tens of thousands of years, the plant community of Triassic Pangaea's interior was undergoing a transformation that would have been unrecognizable to an observer familiar with the earlier landscape. New river systems formed, cutting channels through the ancient red sediment. These rivers were not the slow, meandering streams of an established landscape. They were young, vigorous, carrying enormous sediment loads scoured from the freshly exposed terrain, depositing their burden and spreading fans wherever their gradient decreased. They were also connected, linking the coastal systems to the interior in ways that had not been possible before, creating corridors for the movement of aquatic organisms and the animals that depended on them. Lakes formed in every depression. Not planned, not slowly but spontaneously, wherever water could collect faster than it evaporated. Some were ephemeral, lasting only a season before drying back to mud. Others were more permanent, fed by reliable river systems, deep enough that their bottoms stayed wet even through the dry season. These lakes became focal points for animal activity, the ancient equivalent of oases, concentrating populations of animals from the surrounding terrain and supporting communities of aquatic organisms that had no way to exist in the arid landscape that preceded them. For the animals of the late Triassic, this climate shift was both catastrophe and opportunity, depending on what they had been adapted to. The drought specialists struggled. Animals with physiologies tuned to water conservation, with behavioral strategies built around seasonal drought, with breeding cycles that depended on the drying of temporary pools, found the constant moisture as hostile in its own way as a desert. The rhynchosaurs, those enormously successful seed-eating herbivores that had dominated many Middle and Late Triassic ecosystems, declined sharply during the Carnian pluvial episode. Their particular combination of ecological requirements, the specific plant communities they depended on, the seasonal pattern of their breeding, was disrupted by the changed climate. The Dicynodonts also suffered. These survivors of the Permian extinction had made the Triassic their own, diversifying into dozens of species across multiple continents, occupying the large herbivore role across the landscape. But the Carnian pluvial episode hit them hard. Their diversity dropped sharply in the geological record corresponding to the wetter period. Some lineages disappeared entirely. Others reduced their geographic ranges to the still drier regions that the monsoons did not reach. The age of the Dicynodonts was ending. But for other groups, the rain was transformative in the most positive sense. The archosaurs, and particularly the dinosaurs, responded to the ecological disruption of the Carnian pluvial episode with what can only be described as explosive diversification. The disappearance of the dominant herbivore groups opened herbivore niches, and the lineages of sauropodomorphs, those early long-necked dinosaurs that had been experimenting with plant-eating since the early late Triassic, found themselves with vastly increased ecological space to occupy. The earliest large sauropodomorphs appear in the fossil record precisely during and immediately after the Carnian pluvial episode. Plateosaurus, one of the best-known early dinosaurs, came from this period, reaching lengths of 7 to 10 meters and weighing perhaps 4 tons. Its long neck allowed it to reach high into the new conifer forests that were expanding across the wetter Triassic landscape. Its differentiated teeth were capable of processing the tough conifer vegetation that now dominated many regions. It was not yet the enormous quadrupedal creature that its descendants would become, it was still primarily bipedal, but the trajectory was clear. The theropod dinosaurs were also diversifying rapidly during this period. Small carnivorous theropods, filling the ecological roles vacated by declining archosaur lineages, were appearing at fossil sites across the globe. The predator guild of the late Triassic was in flux, with old dominants declining and new forms taking their places, and the theropods were among the primary beneficiaries of this reshuffling. The Carnian pluvial episode also had profound effects on marine ecosystems. All that fresh water flowing into the oceans through the expanded river systems changed coastal salinity, altered nutrient inputs, and disrupted the chemical balances that marine organisms had adapted to. Some marine groups suffered. Others thrived in the altered conditions. The episode was in many ways as significant for ocean evolution as for terrestrial evolution, though the evidence from marine deposits is less well preserved in many regions. The episode lasted approximately 2 million years. 2 million years of rain. Not constant, not uniform, but persistent and transformative, fundamentally different from the dry world that preceded it. And when it ended, when the volcanic forcing that had driven it began to diminish and the climate slowly began to move back toward drier conditions, the world that emerged was not the same world that had entered the wet period. The species that had dominated before were mostly gone. The species that had been marginal before were dominant now. The stage had been rearranged and the new cast was taking its positions. The dinosaurs were among the new cast. More than that, they were becoming the lead players, the animals around which the other roles were organized. The sauropodomorphs were large herbivores now, filling the roles that the dicynodonts and rhynchosaurs had occupied. The theropods were the primary large carnivores. The ornithischians were beginning to diversify into their own herbivore niches. The framework of the Mesozoic terrestrial ecosystem was being assembled. You are standing at the edge of a lake that did not exist 20,000 years ago. The water is dark and rich with dissolved organic matter from the newly colonized landscape, its surface broken by the rings of fish rising to take insects. The bank is thick with vegetation, ferns and horsetails and young conifers pressing against each other in the abundance of available light and moisture. The air is humid, warm, full of the sounds of a world doing what worlds do when given the resources to be productive. Somewhere in the vegetation behind you, something large is moving. Not threateningly, not quickly, but with the slow deliberate purpose of an animal that weighs several tons and has learned that the world tends to accommodate creatures of its size. You hear the creak of branches, the soft impact of large feet on wet soil. The movement stops. There is a long pause, filled with the sounds of the lake and the wind in the new forest. And then, very quietly, the sound of something eating. The geological evidence for the Carnian pluvial episode is among the most compelling and detailed in the Triassic record. Rock cores taken from sites across Europe, particularly from the Germanic basin, show a clear transition from the red, oxidized sediments characteristic of dry conditions to gray, organic-rich sediments indicative of persistently wet, reducing conditions. This transition occurs at the same level in the geological sequence across dozens of sites, confirming that it represents a global climate event rather than a local or regional phenomenon. The carbon isotope record from Carnian sediments shows a distinctive signature that researchers have interpreted as evidence of massive volcanic carbon dioxide injection into the atmosphere. Carbon has two stable isotopes, carbon-12 and carbon-13, and the ratio between them in organic matter reflects the chemistry of the atmosphere at the time the organic matter was produced. A negative excursion in carbon-13 values, meaning an increase in the proportion of carbon-12, is the signature expected from a large injection of volcanic CO2, which is relatively depleted in carbon-13. This signature appears clearly in Carnian sediments from multiple continents, linking the climate event to its volcanic cause. The palynological record, the pollen and spore assemblages preserved in Carnian sediments, provides detailed information about the plant community changes that accompanied the climate shift. Pollen assemblages from before the episode are dominated by conifer and seed fern pollen types adapted to dry or seasonally dry conditions. During the episode, these assemblages are replaced by assemblages dominated by fern spores, the classic disaster flora of disturbed and wet conditions, followed eventually by new conifer pollen types representing the moisture-tolerant conifer communities that expanded in the wetter climate. The effect of the Carnian pluvial episode on soil chemistry is preserved in the mineral composition of paleosols, ancient soils fossilized in place. Modern soils formed in dry conditions retain calcium carbonate nodules, called caliche, that precipitate from evaporating soil water. Soils formed in wet conditions develop differently, with calcium carbonate being leached out by abundant rainfall rather than concentrated by evaporation. The shift from caliche-bearing paleosols to caliche-free, leached paleosols at Carnian sites records the change in soil water chemistry as the climate shifted from dry to wet. The disruption caused by the Carnian pluvial episode did not affect all regions equally. High-latitude regions, where the climate had always been more moderate and less dependent on the stability of the tropical monsoon systems, experienced less dramatic changes than equatorial regions. Some high-latitude communities appear to have been relatively little affected by the episode, their species compositions remaining more or less continuous across the wet interval. This geographic heterogeneity in the severity of the climate impact created a mosaic of refugia and transformed habitats that contributed to the complexity of the subsequent recovery. The marine response to the Carnian pluvial episode is recorded in sediment cores and rock outcrops from what were shallow marine environments at the time. The increase in freshwater input from the expanded river systems is detectable in the isotopic composition of marine carbonates, which record changes in ocean salinity and temperature. The influx of terrestrial nutrients carried by the expanding rivers produced blooms of marine productivity in some coastal zones, the record of which is preserved as dark, organic-rich layers in some marine sediment sequences. These productivity events supported some marine communities even as others were being disrupted by the changed conditions. The timing of the dinosaur diversification relative to the Carnian pluvial episode has been studied in detail by paleontologists analyzing the global dinosaur fossil record. Statistical analyses of dinosaur diversity through the Carnian and subsequent stages show a clear increase in the rate of new species appearance and geographic range expansion during and immediately after the wet interval. This pattern is consistent with the hypothesis that the ecological disruption of the Carnian pluvial episode was the trigger for the dinosaur diversification, though the precise mechanisms remain a topic of active research. The wet world of the Carnian was also a world of newly connected habitats. Before the episode, the interior of Pangaea was divided from the coastal zones by barriers of inhospitable dry terrain that most organisms could not cross. The expansion of river systems and lakes during the wet interval created corridors through these barriers, allowing the dispersal of aquatic organisms into previously isolated interior basins and the movement of terrestrial animals along the newly vegetated river banks. This increased connectivity accelerated the exchange of species between previously isolated regions and contributed to the homogenization of the Carnian biota across broad geographic areas. The ecological impact of the Carnian pluvial episode on insect communities was significant and has been documented through the fossil record of amber and compression fossils preserved in lake sediments from this period. Insect diversity shows a marked increase through the Carnian, with new ecological strategies and new body plans appearing in the record at rates significantly higher than those of the preceding Middle Triassic. The expansion of freshwater habitats was particularly important for aquatic insect larvae, and the diversification of aquatic insect groups during the wet interval contributed substantially to the overall increase in insect diversity. The explosion of insect diversity during the Carnian had downstream effects on all the animals that depended on insects for food, including the small archosaurs and cynodonts that are among the earliest dinosaur relatives. There is a moment in the evening, here in the late Triassic, when the light does something extraordinary. The sun, lower now on the horizon, sends its warmth through a sky that has been partly cleared of clouds by the afternoon wind, and the rays catch the surface of the lake and the upper canopy of the new forests at the same angle, turning both to gold simultaneously. In that light, standing in the open at the forest edge, the early sauropodomorphs are spectacular. Spectacular not because they are yet the enormous creatures they will become. They are large by the standards of the Triassic, significantly larger than anything that preceded dinosaurs in the herbivore role. But they are not Brachiosaurus. They are not Argentinosaurus. They are the beginning of that lineage, the early chapters of a story that will take another 100 million years to reach its most dramatic moments. They are impressive in the way that a foundation is impressive when you understand what it supports. Plateosaurus was one of the most successful and widespread of the early sauropodomorphs. Its fossils found across what is now Germany, France, Switzerland, and adjacent regions of Europe, which in the late Triassic was part of the tropical northern margin of Pangaea. It was a biped, or at least a habitual biped, walking primarily on its two hind legs with its long neck extended forward and upward to browse the higher reaches of vegetation that smaller animals could not access. Its neck was proportionally long, though not yet the extraordinary structure it would become in later sauropods. The bones of the neck were lightly constructed, hollow or semi-hollow, reducing weight while maintaining structural integrity. The small head at the end of this neck was equipped with spatula-shaped teeth, numerous and tightly packed, their surfaces marked by fine serrations that helped them process plant material. The teeth wore down relatively quickly with use, but new teeth grew throughout the animal's life, replacing worn ones in a continuous cycle. The size of Plateosaurus, up to 10 meters in length and 4 or 5 tons in weight for the largest individuals, was itself a significant evolutionary development. Large body size confers several advantages for herbivores. It allows the exploitation of food sources that smaller animals cannot access, high brows being the obvious example. It increases the efficiency of digestion, because large gut volumes give food more time for fermentation. It provides defense against predators that might easily take smaller animals but cannot readily overcome a large one. And it reduces thermoregulatory costs in variable climates, because large bodies have a lower surface area to volume ratio and therefore lose and gain heat more slowly. But large body size also has costs. It requires more food in absolute terms, even if less food per unit of body weight. It requires longer development times, meaning young animals are vulnerable for longer periods. It constrains habitat use, because large animals need large territories and cannot exploit the dense undergrowth and small spaces available to smaller ones. The transition to large body size in the sauropodomorph lineage was not a simple progression in a single direction. It was a negotiation between benefits and costs, resolved differently in different lineages and different environmental contexts. The sauropodomorphs were not the only large herbivores on the late Triassic landscape. The Allosaur, those armored herbivores of the Archosaur lineage, remained important through much of the late Triassic. The surviving Dicynodonts, reduced in diversity but not yet entirely gone, still occupied some herbivore niches in some regions. And the Rhynchosaurs, though declining, had not yet disappeared entirely. The early sauropodomorphs were competing with these established groups even as they were replacing them. The mechanisms of replacement are worth considering. The sauropodomorphs did not simply outcompete the older herbivore groups in direct confrontation. Competition for food between large herbivores of different species is generally an indirect affair, each animal taking what it needs from a shared resource pool, and the group that can exploit more of the available resources more efficiently tends to grow at the expense of others over the long run. The sauropodomorphs were accessing food sources, high brows primarily, that the Allosaur and Rhynchosaurs could not reach. They were expanding the total food resource available to the herbivore community, not simply taking a larger share of an existing one. The long neck was the key innovation. It allowed the sauropodomorphs to reach into the middle and upper levels of the new conifer forests, harvesting the dense foliage there that the shorter-necked herbivores left untouched. This is a strategy that appears repeatedly in the history of animal evolution, the giraffe being the obvious modern example, because it opens a food resource that is effectively unavailable to competitors and that can be very large if the forests are dense. The social behavior of early sauropodomorphs is difficult to determine from fossil evidence, but some tantalizing clues exist. Multiple individuals of Plateosaurus are often found at the same fossil sites, sometimes in groups that seem too concentrated to be the result of random individual deaths. Some researchers interpret these as drowning events, when groups of animals were caught in flash floods and swept into sediment traps. If the animals were traveling together when they died, it suggests at least some degree of gregarious behavior, moving in loose groups if not organized herds. Herding behavior would have been advantageous for animals of this size. A group of several large herbivores moving together provides collective vigilance against predators, more eyes and noses scanning for threats. It also concentrates feeding pressure, which encourages more efficient use of available vegetation and may have driven the animals to move more frequently between feeding areas, which in turn would have distributed their impact across a wider area. Modern mega-herbivores like elephants show sophisticated herd dynamics, and while it would be wrong to assume that early sauropodomorphs had the same complexity of social organization, the ecological incentives for some degree of grouping were present. The predators that hunted sauropodomorphs were themselves evolving. The theropod dinosaurs, still relatively small in the late Triassic, were developing the hunting strategies and anatomical specializations that would define the group for the rest of the Mesozoic. The long, grasping hands with curved claws, the sharp, recurved teeth for cutting meat, the powerful hindquarters for speed and the bipedal stance that freed the hands for prey capture. These features were present in the earliest theropods and would be elaborated on through hundreds of millions of years of subsequent evolution. The coexistence of early sauropodomorphs and early theropods establishes one of the most enduring ecological relationships of the Mesozoic, the dynamic between giant herbivores and the large carnivores that hunted them. It is a relationship built on arms races, each improvement in predator hunting efficiency matched by improvements in prey defense, each increase in prey size met by increases in predator size over evolutionary time. This arms race would drive the evolution of both groups for 165 million years, producing increasingly spectacular animals at both ends of the size spectrum. As the late Triassic progressed and the Carnian pluvial episode gave way to drier conditions, the sauropodomorphs continued to diversify and spread. New species appeared across what is now Europe, South America, Africa, and North America. Body sizes varied across the group, some lineages remaining relatively small and bipedal, others beginning the evolutionary path toward the enormous, obligate quadrupeds that would define the sauropod lineage in the Jurassic. The transition to quadrupedal locomotion in sauropods is one of the most fascinating locomotor evolutionary stories in paleontology. The earliest sauropodomorphs, like Plateosaurus, were essentially bipedal. Their front limbs were much shorter than their back limbs, and their center of mass was positioned over or behind the hips. As sauropod ancestors grew larger, the center of mass shifted forward as the neck and head grew proportionally longer, eventually reaching a point where bipedal locomotion became mechanically impractical and quadrupedal support was necessary. The arms lengthened in response, evolving from the relatively small grasping structures of the biped ancestors to the massive supporting columns of the fully committed quadruped. This transition was not sudden. Intermediate forms existed, animals whose forelimbs were longer than those of typical early sauropodomorphs but shorter than those of fully committed sauropods, animals that could switch between bipedal and quadrupedal locomotion depending on the activity. The fossil record captures some of these intermediates, their body proportions telling a story of gradual biomechanical adjustment across millions of years. The golden light has faded now. The lake is darkening, its surface reflecting a sky that grades from pale yellow at the horizon to deep blue overhead. The sauropodomorphs at the forest edge have moved back into the trees, their large bodies becoming shadows in the dusk. You can still hear them, the soft rumble of digestive sounds, the occasional shift of large feet, the crack of a branch being pushed aside. They are settling for the night, these early giants, these architects of a body plan that will come to define the largest land animals the world has ever seen. The feeding apparatus of early sauropodomorphs was remarkably conservative given the range of food sources it had to process. Unlike later sauropods, which developed enormous skulls with batteries of teeth that could strip leaves from branches with great efficiency, early sauropodomorphs like Plateosaurus had relatively simple leaf-shaped teeth that were suitable for cropping vegetation but could not achieve the throughput of the more derived later forms. They compensated for this limitation through the sheer size of their digestive systems, the enormous barrel-shaped body containing a gut of such volume that even inefficiently processed food yielded sufficient nutrition. Gastroliths, stomach stones, have been found associated with some sauropodomorph fossils, and their presence suggests that these animals, like many modern birds, swallowed stones that sat in a muscular stomach and helped grind up plant material that their teeth could not fully process. The use of gastroliths is a strategy that allows an animal to process tough plant material more efficiently without the metabolic cost of developing and maintaining more complex teeth. It is a behavioral complement to the rather simple tooth morphology of early sauropodomorphs, and together they made herbivory viable at a body size that would have been impossible for an animal dependent on teeth alone for food processing. The bone structure of early sauropodomorphs shows interesting details about their growth and physiology. The cortical bone, the dense outer layer of long bones, contains growth rings similar to tree rings, annual markers of the periodicity of Triassic seasons that can be used to determine the age of an individual at death. Studies of these growth rings in Plateosaurus specimens show that individuals were highly variable in their growth rates, some reaching large body size in 10 years while others of the same species took 20 years to achieve similar size. This variability is unusual and has been interpreted as evidence that early sauropodomorphs had metabolic rates that were sensitive to environmental conditions, growing faster when food was abundant and slower when it was not. The variation in adult body size within Plateosaurus populations is also remarkable. The largest known Plateosaurus specimens are more than twice the body mass of the smallest adults, a degree of size variation within a species that is unusual among modern reptiles but not unheard of in animals with environmentally sensitive growth rates. This variation might reflect differences in the quality and abundance of food available to different individuals in different geographic locations, or it might reflect differences between sexes if Plateosaurus was sexually dimorphic, or it might reflect both. The trackways left by early sauropodomorphs in Triassic sediments are preserved at several sites in Europe and provide information about locomotion that skeletal remains alone cannot offer. The tracks show that Plateosaurus was primarily bipedal when moving, its front feet leaving impressions only when the animal slowed or stopped. The stride length and the spacing between the track series give information about speed and gait. Some trackways show evidence of running, the stride length increasing and the depth of impression decreasing as the animal moved faster and its weight distribution shifted. The late Triassic saw the first attempts at what would eventually become the sauropod body plan, the massive, long-necked, small-headed quadrupeds that would become the dominant large herbivores of the Jurassic. The transition from the relatively compact early sauropodomorphs to the enormous sauropods required a series of anatomical changes that were interconnected in complex ways. The neck had to elongate, which required lightening of the neck vertebrae through air-filled spaces. The body had to increase in size, which required enlargement of the gut and reorganization of the skeletal support. The limbs had to transition from the semi-bipedal arrangement of Plateosaurus to the fully quadrupedal elephant-like columns of later sauropods. The ecological engineering that large herbivores perform is one of the most important but least visible aspects of terrestrial ecosystem function. Modern elephants, which are in many ways the ecological equivalents of the large sauropodomorphs, dramatically alter the structure of African savanna ecosystems by knocking down trees, creating open habitats from closed forest, and cycling nutrients through their enormous digestive systems in ways that benefit other organisms. The early sauropodomorphs of the late Triassic were beginning to perform similar ecological functions, their feeding behavior and physical movement through the landscape altering the structure of the forest in ways that created habitats for smaller species and influenced the evolution of the plant communities they fed on. The world that early sauropodomorphs inhabited was not static. The late Triassic was a period of considerable climatic variation, with regional differences in rainfall, temperature, and seasonality that shifted over time as Pangaea continued its slow fragmentation and the great rifts began to widen into shallow seaways. The sauropodomorphs that thrived in this shifting world were those that maintained the flexibility to move with changing conditions, following the vegetation as it responded to shifting rainfall patterns, colonizing new territories as rifting opened corridors and removed barriers. The anatomy of the sauropodomorph skull tells a story of specialization for a plant-based diet that was being refined through the Triassic. The jaw muscles attached to the temporal region of the skull, and in early sauropodomorphs the temporal fenestrae, those windows in the skull roof that allow jaw muscles to bulge outward during contraction, were of moderate size. In later sauropods, these openings would become very large relative to skull size, indicating the enormous jaw muscles needed to process vegetation at the rate required to fuel a body of tens of tons. The Triassic sauropodomorphs were early in this process, their skull morphology functional but not yet driven to the extremes of their Jurassic descendants. The relationship between early sauropodomorphs and the conifer forests that fed them was not one-sided. The animals that fed on these forests also shaped them in ways that influenced the evolution of the trees themselves. Heavy browsing pressure on the lower and middle branches of conifers selected for individuals that grew faster, that invested more in trunk height to put their foliage out of reach, that produced resin in greater quantities as a deterrent to damage. The very shape of the conifer forests of the late Triassic was being influenced by the presence of these large herbivores, an early example of the coevolutionary dynamic between large herbivores and the plant communities they depend on. The water sources of the late Triassic landscape were gathering points for the large sauropodomorphs in ways that have left their mark in the fossil record. Numerous sauropodomorph fossil sites are associated with ancient lake sediments or river channel deposits, environments where animals congregated around permanent water and where their remains were most likely to be preserved. The concentrations of individuals at these sites tell us something about the behavior of these animals near water, their tendency to come to the same places repeatedly, perhaps drawn by the combination of water availability and the lush vegetation that grew at the margins of Triassic lakes and rivers. The juveniles of early sauropodomorphs present a particularly interesting research question. Young sauropodomorphs would have been much more vulnerable to predation than adults, their smaller size making them accessible to theropod predators that could not effectively attack a full-grown individual. The strategies that young sauropodomorphs used to survive to adulthood are not well understood from the fossil record, but by analogy with modern large herbivores it seems likely that they stayed close to adults, particularly their own parents, using the protection that large body size provided to its adult neighbors as a shield during the most vulnerable early phases of life. The expansion of sauropodomorphs out of their original South American heartland into Europe, Africa, and eventually other regions of Pangaea was one of the notable biogeographic events of the late Triassic. The fossil record shows Plateosaurus and its relatives in Europe, Massospondylus and related forms in southern Africa, and various other sauropodomorph lineages appearing in different regions over the course of a few million years. This spread across the supercontinent was facilitated by the relatively unobstructed land connections that still characterized Pangaea in the late Triassic, before the rift valleys and shallow seaways that would eventually fragment the supercontinent had developed sufficiently to create barriers to dispersal. The night has settled completely now over the late Triassic landscape. The sauropodomorphs at the forest edge have moved deeper into the trees, their large bodies pressing through the undergrowth with a sound like a slow wave, unhurried and thorough. The stars are out above the canopy, brilliant and numerous, the same stars that will be there 250 million years from now but arranged in patterns that no living eye yet knows. The forest breathes around you, the slow exhalation of thousands of trees releasing the day-accumulated oxygen into the cooling air, and in the middle distance, barely audible, the steady rhythmic sound of very large animals breathing in their sleep. All ages end. The Triassic, which had begun in the silence and devastation of the Great Dying and built itself over 50 million years into a complex and diverse world, was approaching its own conclusion. Not with the suddenness of the later Cretaceous extinction, when an asteroid's impact changed everything in minutes. The Triassic ended with a geological event that was in some ways a mirror of what had begun it: volcanic activity on a massive scale, greenhouse warming, disrupted ecosystems, a reshuffling of the biological order. The Central Atlantic Magmatic Province, CAMP as geologists call it, began erupting approximately 201 million years ago as the rifting of Pangaea accelerated. The same forces that were pulling the supercontinent apart were also providing pathways for magma to reach the surface, and the result was one of the largest flood basalt events in Earth's history. Lava flows covered areas of what is now eastern North America, Brazil, Western Africa, and southern Europe, the four crustal plates that were then in contact along the nascent Central Atlantic Rift Zone. The gases that came with those eruptions, the carbon dioxide, the sulfur dioxide, were familiar in their effects. Global temperatures rose. The hydrological cycle intensified. Ocean chemistry changed. The same cascade that had closed the Permian now worked its way through a world very different from the one that had existed 250 million years earlier, but no less susceptible to the disruption of its atmospheric chemistry. The end Triassic extinction was not as severe as the Permian-Triassic event. The Great Dying had been uniquely catastrophic, in a class by itself in terms of the percentage of species lost. The Triassic-Jurassic extinction was devastating, certainly wiping out roughly 50% of species, but it operated against the backdrop of an already complex and diverse biosphere rather than against the stripped and simplified world of the post-Permian. Among the victims were many of the groups that had defined the Triassic. The large Rawasuchian archosaurs, those apex predators that had dominated terrestrial ecosystems for much of the Triassic, did not survive. The Aetosaur, the armored herbivores, went extinct. The phytosaurs, those crocodile-like hunters of Triassic waterways, disappeared entirely. Many of the distinctive marine reptile groups that had been recovering through the Triassic were reduced or eliminated. The ammonoid cephalopods, those valuable geological time markers, went through another severe bottleneck. What is striking about the end Triassic extinction, from the perspective of the story we have been telling, is what it did not eliminate. The dinosaurs survived. Not just survived, they emerged from the extinction event in a position of dramatically increased dominance, almost as if the extinction had been specifically designed to remove their competition. The sauropodomorphs, the theropods, the early ornithischians, all survived, and when the world began its recovery after the extinction event, they found themselves in an ecological landscape with very little competition for the large herbivore and large carnivore niches. The pterosaurs survived as well, and would go on to diversify into their most spectacular forms in the Jurassic and Cretaceous. The crocodilomorphs survived, and would eventually find the semi-aquatic body plan that has sustained them to the present day. The early mammals, the descendants of advanced cynodonts, survived, small and marginal as always, waiting in their burrows and leaf litter for the opportunity that would come 66 million years later. The survival of the dinosaurs through the end-Triassic extinction has been interpreted by some researchers as evidence of genuine superiority of the dinosaur body plan over those of their competitors. The upright posture, the avian-style respiratory system, the potentially elevated metabolism, these traits may have given dinosaurs a resilience in the face of environmental stress that the archosaurs they competed with lacked. This interpretation is appealing but should be held lightly. Survival of mass extinctions often has a significant random component, and it is difficult to demonstrate that dinosaurs survived because of their specific traits rather than because of the accidents of where they happened to be living when the worst effects of the extinction hit. What is certain is that the world that emerged from the end-Triassic extinction was a world dominated by dinosaurs in a way that the late Triassic world had not been. The Jurassic period, beginning approximately 201 million years ago, would see the flowering of the dinosaur empire in all its extraordinary diversity and grandeur. The sauropods would grow to sizes that stagger the imagination, dwarfing even the largest of the late Triassic sauropodomorphs. The theropods would diversify into hunters of every size and strategy. The ornithischians would produce the most bizarre and specialized herbivores the world has seen. The mammals would survive through all of this, small and clever and mostly nocturnal, carrying their warm blood and their differentiated teeth and their increasingly sophisticated brains through 165 million years of dinosaur dominance, waiting. Not consciously waiting. Not with any awareness of the opportunity that was eventually coming. Simply living generation by generation, adapting to the world as they found it, which happened to be a world run by dinosaurs for a very long time. The Triassic then was a transition. It is not usually celebrated as one of the great dramatic periods of geological history, not the way the Cambrian explosion is celebrated, or the Cretaceous with its tyrannosaurs and its dramatic ending. It is often skipped over, a connector between the horror of the Permian extinction and the grandeur of the Jurassic. But this is a misreading of its significance. The Triassic was where the Mesozoic was built, where the dinosaurs found their footing, where the mammals found their blueprint, where the pterosaurs discovered the sky, where the modern oceans began to take their biological shape, where the continents began the slow drift toward the configuration we know today. Every spectacular thing that came after in the Mesozoic was built on foundations laid in the Triassic, in those 50 million years of recovery and experiment and diversification that turned a nearly dead planet back into a living one. The end-Triassic extinction, seen from this perspective, is not primarily a story of destruction. It is a story of selection, of the world choosing, through the blind mechanism of differential survival, which of the many experiments of the Triassic would be carried forward into the next age. The dinosaurs were among those chosen, not through intent or design, but through the accumulated consequence of small advantages that proved, in the end, to matter. The first light of the Jurassic would find a world that looked, in many respects, like a larger, more fully realized version of the late Triassic world. The same basic plant communities, conifer forests and cycads and ferns. The same basic animal groups, dinosaurs and pterosaurs and crocodilomorphs and mammals. But the proportions had changed, the dominant groups were now clearly dominant in ways they had not been before, and the world was becoming, with each passing million years, more unmistakably the world of the dinosaurs. You are standing at the edge of the Triassic, looking forward and backward simultaneously. Behind you, the long slow recovery from the great dying, the patient assembly of ecosystems from almost nothing, the first flights of pterosaurs and the first steps of early dinosaurs. Ahead of you, the grandeur of the Jurassic, the immense forests and the enormous animals and the complex ecosystems that will define the middle of the Mesozoic. You are at the hinge point, in the place where one age hands off to another. The air is warm, and the smell of resin from the surrounding conifers is strong and sweet and ancient. The ground under your feet holds the prints of animals that were here this morning and will be here tomorrow, large three-toed tracks pressed into the soft margin of a stream, marks of a world that is fully inhabited and fully alive and moving, always moving, towards something it cannot see but is becoming nonetheless. The volcanic activity of the Central Atlantic Magmatic Province did not simply pump carbon dioxide into the atmosphere. It also injected sulfur dioxide, which combined with water vapor to form sulfuric acid aerosols that reflected sunlight and caused short-term cooling even as the longer-term CO2 warming was building. This alternation between volcanic cooling and greenhouse warming created a climate system that oscillated rather than simply trending in one direction, and the oscillations may have been particularly stressful for organisms that required stable conditions for reproduction or that had seasonal life cycles tied to predictable temperature patterns. The end-Triassic extinction is recorded with particular clarity in marine sediments because marine environments tend to preserve fossils more reliably than terrestrial environments. The boundary between Triassic and Jurassic sediments in marine sequences is marked by a dramatic change in the ammonoid fauna, the bivalve fauna, and the composition of the microfossil assemblages. The transition happens rapidly in the geological record, within perhaps tens of thousands of years, a blink in geological time. The rapidity of the transition is one of the lines of evidence that the end-Triassic extinction was driven by a catastrophic event rather than a gradual change. The terrestrial record of the end-Triassic extinction is patchier but consistent with the marine record. Plant communities show disruption at the boundary, with the distinctive pollen assemblages of the latest Triassic being replaced by assemblages dominated by fern spores, the classic post-disturbance flora that follows major ecological disruptions. Animal faunas change substantially with the loss of the large non-dinosaurian archosaurs and the replacement of diverse Triassic communities with simpler, dinosaur-dominated communities in the earliest Jurassic. The recovery from the end-Triassic extinction was faster than the recovery from the Permian-Triassic extinction, partly because the end-Triassic event was less severe and partly because the surviving organisms were more complex and therefore capable of rebuilding ecosystems more quickly. The Jurassic world that emerged from the recovery was dominated by dinosaurs in a way that no previous world had been dominated by any single group, and this dominance would persist with only minor interruptions until the end of the Mesozoic. The exact cause of the end-Triassic extinction remains an area of active research. The camp volcanism is the primary candidate, but there is also evidence of a bolide impact at or near the Triassic-Jurassic boundary, and some researchers argue that the impact contributed to the severity of the extinction. The relative contributions of volcanism and impact to the end-Triassic biotic crisis are difficult to disentangle because the two events were approximately contemporaneous, and their effects on the climate and biosphere overlap in ways that current research has not yet fully resolved. The legacy of the end-Triassic extinction was not merely the survival of the dinosaurs and the elimination of their competitors. It also involved the restructuring of biogeographic patterns as the early Jurassic world was repopulated from the survivors of the extinction. The geographic distribution of early Jurassic dinosaurs and other animals was in many cases different from the distribution of their Triassic predecessors, reflecting both the patterns of survival through the extinction and the subsequent dispersal of survivors into newly available territories. The end-Triassic extinction was, in this sense, both an ending and a resetting, a clearing of the board that allowed the game of evolution to continue with a new distribution of pieces. The recovery from the end-Triassic extinction was not merely biological but also geochemical. The massive injection of carbon dioxide by the camp volcanism left a geochemical legacy in the ocean and atmosphere that took millions of years to process. The drawdown of this CO2 through the combination of rock weathering, organic carbon burial, and marine carbonate production was a process that shaped the climate of the early Jurassic in ways that influenced the diversification of the surviving and recovering lineages. The early Jurassic was in some respects warmer and moister than the late Triassic had been, and these conditions were conducive to the rapid expansion of dinosaur populations and the development of the complex Jurassic ecosystems that would eventually produce the most spectacular animals in terrestrial history. The world that crossed into the Jurassic was not simply a diminished version of the Triassic world. It was a world in which certain possibilities had been foreclosed and others opened wide. The enormous Rauisuchians were gone, and with them the particular predatory strategies they had pioneered, their bulk and their sprawling gait and their serrated teeth leaving no successors among the archosaurs. The Atosaur were gone, and the armored herbivore niche they had occupied was empty for a time, waiting for the ankylosaurs and stegosaurs that would fill it tens of millions of years later in the Jurassic and Cretaceous. The landscape was simpler in terms of large animal diversity than the late Triassic landscape had been, but it was simpler in the way that a cleared building site is simpler before the new structure goes up. The dinosaurs that stepped into that simpler world were not the only animals moving to fill the vacated ecological space. The crocodilomorphs, still diverse and ecologically flexible in the earliest Jurassic, were occupying freshwater and coastal environments with a range of body plans and feeding strategies that would take millions of years to sort themselves into the pattern of modern crocodilians. Some early Jurassic crocodilomorphs were still terrestrial, fast-moving predators of small and medium-sized prey. Others were settling into the ambush predator role at the water edge that their descendants have refined over the subsequent 200 million years. The mammals of the earliest Jurassic were small and varied and probably still largely nocturnal, occupying the ecological spaces between the toes of the dominant dinosaurs. But they were not static. The end-Triassic extinction had actually reduced mammalian diversity somewhat, eliminating some of the more diverse and specialized cynodont lineages that had been experimenting with different ecological strategies in the late Triassic. The mammals that emerged from the extinction bottleneck were less diverse in some ways, but the lineages that survived were robust, and they would diversify through the Jurassic into an impressive range of body plans and ecological strategies, including, by the late Jurassic, forms as diverse as small insectivores, aquatic swimmers, and even small gliders. The plant communities of the earliest Jurassic reflected the disruption of the extinction event. Pollen records from the Triassic-Jurassic boundary show the classic pattern of mass extinction disruption, a brief but marked increase in fern spores, the fern spike, that records the rapid colonization of disturbed landscapes by pioneer vegetation before the more complex forest communities could re-establish themselves. The fern spike is a marker of ecological disruption, a signal in the geological record of the kind of rapid landscape change that follows major perturbation, and its presence at the Triassic-Jurassic boundary confirms the severity of the extinction event in terrestrial ecosystems. The early Jurassic recovery of plant communities set the stage for the elaboration of the dinosaur-dominated terrestrial ecosystems that would characterize the Middle and Late Jurassic. The expansion of conifer forests across the northern regions of the separating continents created the food base that allowed sauropodomorphs to grow into the enormous sauropods of the Jurassic. The diversification of ground-level vegetation in tropical regions supported the evolution of specialized small herbivores and the small predators that hunted them. The basic architecture of the Jurassic terrestrial ecosystem was being assembled in the earliest Jurassic from the components that the Triassic had prepared. The rifting of Pangaea that had been contributing to the end-Triassic volcanism continued through the early Jurassic, gradually widening the central Atlantic basin and separating the northern and southern components of the supercontinent. This geographic separation would, over tens of millions of years, create increasingly distinct faunas in the northern Laurasia and southern Gondwana portions of the former supercontinent, driving the regional diversification of dinosaur lineages that makes the Jurassic such a rich subject for paleontological study. The geological process that had helped end the Triassic was simultaneously laying the foundation for the biogeographic patterns that would define the Jurassic. The Triassic, seen from the vantage point of the early Jurassic world it produced, was a necessary crucible. It was the period in which the components of the Mesozoic world were assembled, tested against the harsh realities of post-extinction conditions, and refined into forms capable of sustaining the elaborate ecosystems of the next 150 million years. The 50 million years of the Triassic were not simply a prelude to the dinosaur age. They were the foundation on which the dinosaur age was built, layer by layer, innovation by innovation, survivor by survivor. You are standing for a moment in the earliest light of the Jurassic. The sky above is the same sky that covered the Triassic, the same stars in their slow drift, the same sun beginning its daily arc. But the world below that sky is changed. The large archosaurs that defined the late Triassic landscape are mostly absent. In their place, moving through the recovering forests and across the open plains near the new coasts of the forming Atlantic, are the early representatives of the dynasties that will define the next age. They are smaller than their eventual descendants, less elaborate, less specialized. But they are there, and they are moving, and the world is once again full of the sound and the smell of life. The Triassic has ended. The age of the dinosaurs in its full and extraordinary expression is about to begin. Every world leaves behind a legacy in the world that follows it. Not as intention, not as gift, but as consequence, the accumulated effect of all the things that happened, all the organisms that lived and died and evolved, all the ecological relationships that were established and refined, all the physical and chemical changes that accumulated in the rock and the atmosphere and the ocean chemistry. The Triassic's legacy is among the richest and most far-reaching in the history of life on Earth. Consider the legacy of the dinosaurs themselves. The Triassic established the dinosaur body plan, that upright stance and those hollow bones and that avian-style respiratory system, and gave the lineage its first 50 million years of diversification. The Jurassic and Cretaceous dinosaurs that we know from their spectacular fossil remains were built on that Triassic foundation, and every Tyrannosaurus rex and every Brachiosaurus and every Velociraptor had ancestors in the modest, marginal animals of the Triassic interior. The pterosaurs too carried forward a Triassic inheritance. Those first small, long-tailed flyers of the late Triassic gave rise, over the next 160 million years, to the most spectacular aerial fauna the world has ever seen. Quetzalcoatlus, from the late Cretaceous of Texas, had a wingspan of 10 to 12 meters and is often cited as the largest flying animal in Earth's history. Standing on the ground, it would have been as tall as a giraffe. Its Triassic ancestors had wingspans measured in tens of centimeters. The scale of the journey between those two endpoints is a measure of the evolutionary potential that the Triassic released. The crocodilomorphs, those flexible and adaptable archosaurs whose Triassic representatives ranged from bipedal terrestrial runners to early semi-aquatic ambush hunters, eventually settled on a body plan that has proven among the most durable in vertebrate history. Modern crocodilians are essentially Mesozoic animals living in the present, their basic body architecture unchanged in its essentials for over 80 million years. The Triassic established the lineage and began the experiments that would eventually converge on that extraordinarily successful plan. The mammals have the deepest Triassic roots of all the major modern vertebrate groups. The cynodonts and their immediate descendants, the earliest true mammals, represent the Triassic's most consequential evolutionary contribution to the modern world. Everything about the mammalian body plan, the warm blood and the hair and the differentiated teeth and the complex brain and the extended parental care, was being assembled through the Triassic in the various cynodont lineages, each feature accumulating incrementally, each increment providing some advantage that was retained by natural selection. The marine legacies of the Triassic are less immediately visible but no less significant. The recovery of marine ecosystems through the Triassic established the basic architecture of the complex marine food webs that would characterize the Mesozoic and, in modified form, persist to the present day. The re-establishment of reef-building ecosystems in the Tethys, though using organisms different from modern corals, paved the way for the eventual evolution and proliferation of scleractinian corals, the modern reef builders, which appeared near the end of the Triassic and would build the great reefs of the Jurassic and Cretaceous. The marine reptile dynasties that the Triassic inaugurated, the ichthyosaurs and the plesiosaurs and their relatives, would dominate the oceans for most of the Mesozoic, filling the large predator roles that today are occupied by sharks and killer whales and sperm whales. Their diversity and abundance in Jurassic and Cretaceous seas was extraordinary, a measure of the ecological opportunity that the post-extinction ocean offered and that the Triassic survivors seized. The insects are perhaps the least celebrated but most significant beneficiaries of the Triassic recovery. Insect diversity exploded through the Triassic as the recovering plant communities provided new food sources and new habitats, and by the end of the period the basic outlines of modern insect diversity were in place. The beetles, already beginning their extraordinary diversification in the Triassic, would eventually become the most species-rich order of animals on Earth. The flies, the wasps, the true bugs, all the major insect orders that define modern terrestrial ecosystems, were represented in the Triassic fauna in forms recognizably related to their modern descendants. The Triassic also established patterns of geographic distribution that shaped evolution for millions of years afterward. Pangaea was still largely intact through most of the Triassic, which meant that organisms could and did disperse across the supercontinent, producing the widespread distribution of many Triassic species. But the rifting that was beginning to crack Pangaea apart was creating the first barriers, the first separation of previously connected populations, the first opportunity for geographic isolation to drive divergence between lineages. These early separations planted the seeds of the continental biogeographic patterns that would develop through the Jurassic and Cretaceous as the continents drifted to their modern positions. The vegetation of the Triassic established the framework within which terrestrial animal evolution operated for the rest of the Mesozoic. The conifer-dominated forests that expanded through the Triassic, particularly after the Carnian pluvial episode, would characterize terrestrial vegetation through the Jurassic and much of the Cretaceous. These forests drove the evolution of specialized herbivores capable of processing tough, resin-rich vegetation, and the evolutionary arms race between conifers and herbivores was a major engine of diversification in both groups. The coal beds that accumulated in the swamps and wetlands of the Carnian pluvial episode represent a literal legacy, a physical deposit of organic carbon locked in the rock that records the extraordinary productivity of that brief wet period. Some of these Triassic coal deposits are mined today, making the productivity of those ancient forests a resource for the modern world in a direct and tangible sense. The amber deposits of the Triassic, the hardened resin from those ancient conifers, preserve a microscopic world of extraordinary richness. Insects, mites, plant fragments, fungal spores, all captured at the moment of their encounter with a sticky resin seep on an ancient bark surface and held there in molecular suspension for 230 million years. Each amber specimen is a window into the Triassic world at a scale of detail that no other preservation process can match, and the information locked in these amber windows continues to surprise and inform researchers with every new specimen studied. The Triassic, then, was not merely a transition or a recovery period. It was a creative era in the deepest sense, a time when the biosphere was producing novelties at an extraordinary rate, when the empty ecological landscape left by the Great Dying was being filled with experiments that were bold and various and largely successful. The dinosaurs were the most spectacular of these experiments, but they were not the only ones, and the world of the Triassic was richer and stranger and more full of evolutionary drama than its relatively quiet place in the popular imagination suggests. We are, in a meaningful sense, children of the Triassic. The mammalian body plan that we carry was assembled there. The ecological relationships that shaped mammalian evolution through the Mesozoic were established there. The very concept of a terrestrial ecosystem dominated by large, active, warm-blooded vertebrates was a Triassic invention. When the dinosaurs eventually died and left their world to the mammals, they were leaving it to animals whose blueprint had been drawn in the Triassic, tested through the entire subsequent history of the Mesozoic, and refined into the extraordinary adaptive radiation of modern mammals. The children of the Triassic are everywhere. In the birds that are the living dinosaurs, carrying the hollow bones and the avian respiratory system of their dinosaur ancestors. In the crocodiles that still lurk in tropical rivers, little changed in their essentials from their Mesozoic predecessors. In the lizards and snakes that trace their ancestry to Triassic lepidosaurs. In the turtles that still pull themselves onto sunny rocks in the posture of progonocales. And in ourselves, warm-blooded and large-brained and dependent on parental care, bearing in our biology the marks of the cynodonts that moved through Triassic leaf litter 230 million years ago. The legacy is not abstract. It is embodied, incarnate, living and breathing in the present world. Every time you hear a bird sing, you are hearing a descendant of the dinosaurs, a lineage that traces directly back to the small theropods of the late Triassic. Every time you look at a crocodile, you are looking at an animal that has inhabited a world of dinosaurs and outlived them, carrying forward the archosaur heritage of the Triassic. Every time you feel your own warm-blooded metabolism keeping you active on a cool morning when a lizard would be sluggish, you are feeling the Triassic legacy in your own body. The evolutionary innovations of the Triassic continue to influence the world in ways that are often invisible but pervasive. The nitrogen cycling that occurs in modern soils is driven partly by the same groups of microorganisms that were developing their ecological roles in Triassic soils. The mycorrhizal networks that connect tree roots in modern forests are the descendants of similar networks that were helping Triassic plants access nutrients in recovering post-extinction soils. The basic functional ecology of terrestrial ecosystems, the way energy and nutrients move through food webs and soil communities, was established in its modern form during the Triassic. The history of the Triassic has lessons for the present that are both sobering and, in a qualified way, reassuring. The sobering lesson is that the biosphere is capable of catastrophic collapse when pushed beyond certain thresholds, and that the Great Dying was driven by a process, greenhouse gas injection by volcanism, that has its modern counterpart in anthropogenic carbon dioxide emissions. The rate of current carbon dioxide increase is in some estimates faster than the rate during the Permian-Triassic crisis, and the biosphere is already showing signs of stress that, while currently far less severe than the Permian crisis, are moving in the same direction. The qualified reassurance is that life survived and recovered. Not every species survived, obviously, and the recovery took tens of millions of years, time scales that are meaningless in human terms. But the biosphere as a system was not permanently damaged. It rebuilt itself, produced new forms, new relationships, new levels of complexity. The capacity for recovery is real, even if the time scale of recovery is incompatible with the expectations of any human civilization. The Triassic also teaches us that evolution does not simply repeat itself. The world that emerged from the Triassic was not a restored version of the Permian world. It was something genuinely new, structured by the particular organisms that had survived and the particular conditions under which they recovered. Dinosaurs did not exist in the Permian. Pterosaurs did not exist before the Triassic. The modern forms of crocodilians and turtles did not exist before the Triassic. These groups were not restored from some template that the extinction had erased. They were invented by the conditions of the recovery, by the particular combination of survivors and empty niches and changing climate that defined the Triassic experience. For those of us who find meaning in the deep history of the planet, the Triassic offers both perspective and a kind of kinship. The creatures that moved through the Triassic world were not our ancestors in any direct sense, most of them. But they were part of the long chain of life that led to us. The cynodont foraging in the leaf litter was laying down the framework of mammalian biology. The early dinosaur running through the late Triassic scrub was the distant ancestor of every bird that sings outside your window. The Triassic is not foreign history. It is part of our history, our deepest history, written in the rocks of every continent and in the biology of every living thing. The amber that the Triassic forests produced, the resin that hardened and preserved small fragments of the ancient world, is perhaps the most evocative physical legacy of the period. To hold a piece of Triassic amber, should one be fortunate enough to encounter such a thing, is to hold a piece of the actual Triassic world, a material that was liquid 230 million years ago and that, through the accidents of chemistry and burial and geological survival, has persisted to the present. The insects sometimes preserved inside are individuals, specific animals that lived specific lives in specific places on the Triassic landscape, now accessible to the microscopes and CT scanners of modern science. The techniques that modern science uses to read the Triassic record are themselves the product of accumulated evolutionary intelligence, the same biological process that built the animals and plants we study. The electron microscopes that reveal melanosomes in fossil feathers, the mass spectrometers that analyze carbon isotopes in ancient rock, the CT scanners that reveal internal bone structure without destroying specimens, these are the instruments of a species that inherited from its Triassic cynodont ancestors a brain capable of the kind of systematic inquiry that transforms rock into knowledge. The irony is exquisite, that the descendants of the small insectivores that survived the Triassic are now using their evolved cognitive capacity to understand the world those insectivores inhabited. The geological record of the Triassic is itself a legacy of a different kind. The rock formations deposited during the Triassic now contain the evidence that allows us to reconstruct the period, to walk back through geological time and see something of what the world was like when the dinosaurs first appeared. These rocks are found on every continent, in road cuts and canyon walls and coastal cliffs, patient archives of ancient conditions waiting for curious minds to decode them. The science of paleontology, itself a product of the evolved intelligence that traces back to Triassic cynodonts, is the instrument we use to read these archives. The trace fossils of the Triassic, the footprints and burrows and feeding marks left by organisms in ancient sediments, often tell us more about behavior than body fossils can. A footprint is a moment, a single instant of movement captured in the permanence of rock. A trackway is a story, a sequence of moments that tells you something about where an animal was going and how fast it was moving and whether it was alone or part of a group. Triassic trackways from what is now the eastern United States, Europe and South Africa record the movement of early dinosaurs across the landscapes of the supercontinent, and the patterns they preserve are those of alert, active animals moving through a world that was increasingly theirs. The question of what Triassic animals looked like in life is one that continues to be refined by new research. The discovery that many dinosaurs, including their non-avian descendants into the Cretaceous, had complex integument including feathers or feather-like structures has changed the way we visualize even the earliest dinosaurs. While direct evidence for feathers in Triassic dinosaurs is limited, the phylogenetic inference is clear enough that we can reasonably assume that many early theropods and possibly other dinosaur groups had at least some form of filamentous covering. The vivid, scaly reptiles of popular illustration are almost certainly less accurate than reconstructions that show these animals with the complex, colorful integument of their descendants. The sounds of the Triassic world are entirely lost to us. Sound does not fossilize, and the acoustic ecology of any prehistoric environment is a matter of inference rather than evidence. We can reason from the anatomy of Triassic animals about what kinds of sounds they might have produced and detected. Insects with sound-producing organs could have created the background drone of an ancient landscape. Amphibians gathered around Triassic ponds would have added their calls to the acoustic environment. Early archosaurs, including the dinosaur lineage, may have been capable of some form of vocalization, though the complex vocal apparatus of modern birds was still far in the future. What the Triassic sounded like is a question that paleontology cannot directly answer, but the imagination fills that silence with a richness that feels, somehow, appropriate to the period. The Triassic has a particular significance in the story of how we understand the history of life on Earth. It was during the intensive study of Triassic rocks and fossils in the 19th and 20th centuries that many of the foundational concepts of paleontology were developed and tested. The recognition that mass extinctions were real events, not artifacts of an incomplete fossil record. The understanding that major faunal turnovers occurred at geological boundaries. The realization that the early Mesozoic was a time of rapid and fundamental change in the composition of terrestrial and marine faunas. These insights, developed in large part through the study of Triassic material, shaped the conceptual framework of modern paleontology in ways that persist to the present. The current pace of species loss on Earth has been compared to the mass extinctions of the geological record, and the comparison is not entirely hyperbolic. The rate of species extinction occurring now is estimated by many researchers to be orders of magnitude above the background extinction rate that characterizes periods of relative stability in the fossil record. Whether the current extinction event will reach the scale of the Triassic-Jurassic extinction, let alone the Permian-Triassic event, is a question that depends on choices being made now and in the coming decades. The Triassic record tells us both that recovery from even catastrophic extinction is possible and that the time scale of that recovery is measured in millions of years, not in the decades or centuries that are relevant to human planning and decision-making. The recovery of the biosphere after the Permian extinction required not just the survival of enough species to re-establish ecological function, but the evolution of new relationships between the survivors. The organisms that survived the Great Dying did not simply slot back into the ecological roles that had existed before the extinction. They found new roles, established new relationships, and eventually built an entirely different kind of world. The Triassic teaches us that recovery from mass extinction is not restoration but reinvention, and that the new world that emerges from catastrophe is not a degraded version of the old one but something genuinely different, shaped by the particular survivors and the particular conditions of the recovery. It is night now in the Triassic. The sun has dropped below the western horizon and the sky above Pangaea is doing what all skies do when the world's rotation carries them away from the light, deepening through shades of blue into the profound darkness that comes only when there is no city glow, no artificial light, no human presence at all to soften the transition. The stars that emerge are the same stars, arranged in the same constellations, that will be visible from the same sky 230 million years from now, though no one there will be able to name them yet. You are lying on your back on the warm red soil of the Triassic, and the ground beneath you still holds the heat of the day. The rock that has been absorbing sunlight since morning releases it now, slowly and gently, a warmth that rises through the soil and against your back like the warmth of a living thing. The air is cooling, losing the sharp edge of the day's heat, settling toward the temperature that the night will maintain until the first light begins to grow again in the east. The sounds of the Triassic night are different from the sounds of the day. The large animals that were visible in the late afternoon have retreated, some into the forest, some into the shadow of rock formations, some simply standing quietly in the open with their large eyes turned toward the sound of anything that moves. The predators are more active now, their passage marked by the occasional distant crash of something startled into flight, the brief sound of pursuit and then the specific silence that follows when a hunt ends. Closer to you, the small sounds of the nocturnal world are busy and constant. The cynodonts are out, moving through the darkness with the confidence of animals whose world this is. Their eyes are large, adapted for low light, and they navigate by a combination of vision and an acute sense of smell and those whiskers that trace the contours of the ground before them. You can hear them in the leaf litter nearby, the small sounds of their passage, the occasional pause when something interesting is found. Insects are everywhere in the dark. Their calls form a continuous background, a frequency that sits at the edge of hearing and runs like a current through all the other night sounds. These are not the sounds of modern crickets. Not exactly. The evolutionary lineages that produced those familiar sounds had not yet fully assembled themselves. But there are sounds, complex and layered, produced by animals that have been making sounds at night for longer than there have been ears sophisticated enough to hear them with appreciation. Above you, against the stars, something moves. A pterosaur, catching the last of the thermal lift from the warm ground, making its unhurried way to wherever pterosaurs go when the day is done. Its wingspan is invisible against the darkness, but you can hear it, a soft rhythmic sound that is not quite the sound of any bird wing you have ever heard, something slower and more deliberate, a sound that belongs to a different physics of flight than the birds that will eventually replace this lineage. The lake nearby is producing its own sounds, the water moving in its shallow margins, the occasional splash of a fish or a nocturnal reptile investigating the shallows. Frogs, or at least early amphibians that occupy a similar ecological role, are calling from the reedy edges, their voices high and insistent, a sound that has been continuous near water since the Devonian and that will continue without significant interruption until the last body of water on the planet finally dries under an expanding sun 5 billion years from now. You are very small here. The cosmos has a way of making that clear on nights like this, when the sky is fully opened and the stars are dense and the horizon is a long dark line with nothing human-made to interrupt it. You are small in space and you are small in time, a moment of awareness in a universe that has been running for 13 billion years and will run for vastly longer, a biological event in a planetary history that has already seen catastrophes and recoveries that make everything in human experience seem brief. And yet, the awareness you carry, the capacity to look at this ancient sky and feel something, the ability to hold in your mind the image of this world 230 million years removed from the one outside your window, the sense of connection to the small creatures moving through the Triassic dark, this is also something. It is something that did not exist in the Triassic, something that would not exist for most of the subsequent geological history of the Earth. Consciousness, complex and self-aware and capable of reaching backward through time into worlds it has never inhabited, is a development so recent and so strange that the Triassic would not have recognized its possibility. But it grew from the Triassic. From the cynodonts moving through this night, from the differentiated teeth and the expanding brains and the warm blood that would eventually, through hundreds of millions of years and countless generations, produce the nervous systems capable of this kind of reach. The thought that is thinking itself in your mind right now, the one that is connecting you to this ancient night, is in a real sense the product of a process that was already running here, in these small and unimpressive animals, 230 million years ago. The warmth from the ground is steady and good against your back. The star-filled sky above you is both ancient and immediate, both impossibly remote and entirely present. You are breathing the same basic atmospheric chemistry that the cynodonts and the pterosaurs and the early dinosaurs are breathing all around you in the Triassic dark, oxygen and nitrogen in proportions not too different from your own, the breath of a living planet circulating through the lungs of creatures that will eventually, through long chains of descent and transformation, lead to you. The night has its own rhythm, slower than the day, more patient. The cooling air settles into the low places, the valleys and the riverbanks, creating subtle temperature gradients that influence where animals choose to rest. The large sauropodomorphs you heard moving in the forest at dusk are quiet now, their enormous bodies losing heat slowly in the dark, their metabolisms ticking over at some lower rate than during the activity of the day. They will be still for many hours. The early mammals, those small, furred, warm-blooded descendants of cynodonts that are among the most recent evolutionary innovations on this night's landscape, are active through most of the dark hours. Their elevated metabolisms keep them warmer than the night air and more active than the cold-blooded animals around them, a significant advantage in the nocturnal world. They are eating constantly, as small, fast-metabolizing animals must, converting insect calories into mammalian energy with the patient urgency of animals that cannot afford to slow down. Let your thoughts slow with the night. Let the sounds of this ancient world, the insect chorus and the water sounds and the distant movements of large animals in the dark, settle into something like a background, like the sound of rain or the sound of wind, present but not demanding attention. The Triassic is not asking anything of you. It is simply here, complete and indifferent and full of its own life, offering itself as a place to rest inside while your body does the repair work of sleep. The stars are moving, of course. Not quickly enough to see in any single moment, but the rotation of the planet is carrying them slowly across the sky in their ancient arcs. In the east, the sky is still fully dark, hours before the first suggestion of dawn. The night has not reached its deepest point yet, that late dark hour when the temperature is lowest and the nocturnal animals are most active, but it is moving toward it, patient and unhurried as all nights are. Something small is very close to you now. You can hear it in the leaf litter perhaps 2 meters away, a faint, careful sound of small locomotion through dry material. A cynodont, perhaps, or one of the small archosaurs that occupy the insectivore niche in this ecosystem. It stops when you shift slightly, its small nervous system computing threat from the disturbance. You lie still, and after a moment the sound resumes, the animal having concluded that you are not something it needs to concern itself with. This is, in its small way, an extraordinary thing. A creature 230 million years removed from the world you inhabit, and yet the basic transaction between you, the assessment of threat, the decision to continue or flee, is one you both understand. You share more with it than not. The same basic vertebrate body plan. The same reliance on oxygen. The same drive to eat and be warm and avoid death. The gulf between you is measured in time, not in the fundamental architecture of being alive. The Triassic night holds you gently. The world is ancient beneath you and vast above you and busy all around you with the small ongoing business of life, and you are part of it, briefly and entirely, a warm body in the dark on a planet that is still in the process of becoming what it will be. Let that be enough. Let the sounds of the ancient world be the last sounds you hear as wakefulness loosens its hold and the darkness inside your eyes deepens to match the darkness of the Triassic sky. Rest now. The cynodont is finding its way home. The pterosaur has settled on its roost. The lake is murmuring quietly at its edges. The large animals in the forest are breathing slowly. The stars are moving in their patient arcs. Everything that is alive in the Triassic is doing what living things do at the deepest point of night. And so can you. The thermal mass of the Triassic Earth, heated throughout the long warm days and releasing that heat slowly through the nights, creates a stability of temperature that modern nights in temperate regions do not always possess. You are warm in a way that is not just physical but temporal, connected through the ancient rock to a heat budget that has been accumulating since the sun rose this morning and will be releasing itself slowly until the first gray light appears in the east again. This warmth is patient. It does not hurry. The stars above are moving, of course, though too slowly to see in any single moment. The rotation of the Earth carries them in arcs across the sky, each one following the path that the planet's spin assigns it, rising in the east and setting in the west with the mechanical regularity of a universe that operates by consistent rules regardless of what is happening on the surface of the small rocky world below. These same rules, this same rotation, will carry different stars over different continents in different arrangements 230 million years from now, but the mechanism will be the same. There is a particular quality to the darkness of a world without artificial light. It is not merely darker than what you might experience in a modern countryside night. It is darker in a way that changes the character of perception, that makes the eye give up its primary role to the ear and the nose, that makes the boundary between self and surroundings less distinct. In this darkness, the sounds that mark the Triassic night, the insect chorus, the water sounds, the occasional movements of animals in the dark, are not background. They are the world, comprehensive and surrounding. The cynodont has found its burrow. You do not see this, but you sense it in the way the small sounds near you cease, replaced by the deeper silence of an absence rather than the active silence of a present animal choosing to be still. The burrow is perhaps 50 centimeters below the surface, a passage that turns twice to prevent the entry of cool air, opening into a chamber the size of a human fist, lined with whatever dry plant material the cynodont has collected. Inside, the temperature is several degrees above the surface night air, held there by the insulating properties of the soil above. Everything that is alive tonight in the Triassic will, in 230 million years, be dust. The cynodont and the pterosaur and the early dinosaur and the insects in the dark, all of them will be gone in any meaningful biological sense long before the first hominid looks at a night sky and wonders about the stars. And yet they are here now, completely real, completely themselves, carrying within their warm or cool bodies the entire history of life that preceded them and the entire potential of life that will follow. They do not know this. They are simply alive, which is enough. Sleep comes for warm-blooded animals the way it comes for everything that has a nervous system complex enough to need it. The brain requires rest, the consolidation of the day's information, the maintenance of the cellular infrastructure that makes thought possible. The cynodonts sleep. The early mammals sleep. Even some of the large archosaurs, in the deeper sense of reduced metabolic activity and minimal responsiveness to stimulation, may have something like sleep. In this, the Triassic night is like every other night on a living planet, full of organisms taking the rest that makes tomorrow possible. Let this night be enough. The ancient world is all around you, immense and alive and patient, and you are a small warm presence at its edge, neither more nor less significant than the cynodont in its burrow or the pterosaur on its roost. You are here. You are breathing. The ground is beneath you and the stars are above you and the sounds of life are all around you. That is the whole of it, and it is sufficient, and it is beautiful in the way that only real things, only living moments in living worlds, can be beautiful. Let that be the last thought before sleep. Let it dissolve into the breathing of the ancient night. The breathing of the ancient world around you is the breathing of a planet that has been alive for 4 billion years and will be alive for 4 billion more. The individual organisms in the dark, the cynodont in its burrow, the pterosaur on its roost, the early dinosaur in the shadow of a rock formation, are themselves temporary lives of years or decades against the backdrop of millions and billions. But the process that produced them, the self-replicating, evolving, diversifying, adapting process of life, is far older and far more persistent than any individual, and its breath, its collective breath, is what you are listening to in the Triassic night. You are held between two immensities, the immensity of the past, 230 million years of it behind you, stretching back through the Triassic and the Permian and the Carboniferous to the first cells and the first chemistry, and the immensity of the future 230 million years forward to the world outside your window, and beyond that to whatever comes after as far as the universe allows. In this held place, in this particular moment of rest, the scale of things is not frightening. It is simply true, and in being true, it is a kind of comfort, the comfort of belonging to something enormous. Thank you so much for watching. If you would like to see more videos like this, please consider leaving a like and subscribing to the channel, as it really helps us continue making more content. Anyways, see you in the next one. The Triassic is behind you now, or around you, or underneath you, depending on how you think about deep time. The red soil and the warm dark and the small creatures moving through the ancient night are still there, 230 million years away, carrying their evolutionary potential forward in every heartbeat. The world they were building is the world that built you. Let that thought be a quiet thing, something to carry into sleep rather than to turn over and examine. It does not need your attention right now. It has been waiting for 230 million years. It can wait until morning. The sounds of the ancient world are growing softer now. The insect chorus is becoming a hum, a background frequency at the very edge of hearing. The water sounds from the lake are fading to something like the sound of breathing, slow and even and continuous. The warmth from the Triassic ground is the warmth of a comfortable bed, steady and patient and reliable. You are not in the Triassic, of course. You are in your own time, in your own place, in your own bed, and the sounds around you are the sounds of the present world, traffic or wind or the particular silence of late night and wherever you are. But something of the ancient world is still available to you, in the architecture of your own body, in the warm blood moving through your veins, in the bones that trace their origin to the first upright bipeds of the Triassic, in the brain that is even now processing sensation and memory and the edge of dreaming. Let sleep come. Do not reach for it. It will come the way night comes, gradually and then completely, the light fading from inside as the body moves from the edge of sleep into sleep itself. The Triassic is a long way away. You are right here. And right here, right now, is exactly where rest is. Breathe. The world is ancient and enormous and full of life, and it is also, right now, very quiet. And you are part of it, briefly and entirely, a warm body in the dark on a spinning world. Let that be the last thought. Let it dissolve into the background hum of simply being alive, like an insect sound in an ancient forest, present and continuous and requiring nothing more from you than the simple act of listening. If you like this video, let me know where in the world you are watching from and what time it is. I'm always curious about that. And if you have a suggested topic for the next story, feel free to leave it in the comments below.